warm good morning, one and all present here. We welcome all our honorable members and every participant for 2 days national seminar for earthquake forecasting prediction in Northeast India, that is EAP FNI 2023. We have with us the chairman of event, Professor BP Mishra, Dean, School of Earth Science and Natural Resource Management, chief guest of event, Professor Prabhakar Rath, Vice Chancellor, Mizoram University, guest of honor, Mr. Anmol Srivastav, IAS, Additional Secretary, Disaster Management and Rehabilitation, Government of Mizoram. Now I request the chairman, Professor BP Mishra, Dean, School of Earth Science and Natural Resource Management, to give the welcome note. Yes, sir. You have to hold this one.
I can go there.
Okay, sir.
रहने रोड पर
अच्छा
क्या ऐसे करता है माइक
Sir, for YouTube.
दिस
Yeah, this one.
ठीक है वेरी गुड मॉर्निंग टू एवरीवन प्रेजेंट इन दिस हाउस दिस इज ए वेरी ऑस्पिशियस occasion on behalf of the School of Earth Sciences and Natural Resources Management, Mizoram University, and also on my personal behalf, I warmly welcome the dignitaries on the dais, our Honorable Vice Chancellor, Professor Prabhakar Rath, as a Chief Guest, sir. I welcome you. Guest of honor, Mr. Anmol Srivastav, IAS Additional Secretary, Disaster Management and Rehabilitation, Government of Mizoram. I honor you and I welcome you on this occasion. The coordinator or in charge of the Center for Disaster Management, MZU, Professor BP Sati. I think he is a convener also of this program. He is the part of the system. I express my honor to you. The organizing secretary, the senior faculty in the Disaster Management Center, Dr. Laldin Puya. I welcome you. Or I can honor you. Welcome to for outside persons. And one more faculty, Jonuna. Dr. Jonuna, earlier he was in the HRDC and further joined the center. Okay, I welcome you. And distinguished resource persons from in and outside the Mizoram University. And because some new faces are here, so sir, I welcome you. And faculty colleagues from Mizoram University, research scholars, students, media person if any, and supporting staff, all are most welcome on this occasion. As a dean, I would like to give brief introduction about my school. We are having the 6 academic departments: Department of Environmental Science, Department of Forestry, Department of Extension, Education and Rural Development, Department of Geology, Department of Geography and Natural Resource Management. And besides that, we are having 3 centers and they are working very excellently in the area of research. Center for Disaster Management, Center for Biodiversity Research, and Center for Petroleum Exploration. So this is the huge school in the Mizoram University. and the theme of the program is the earthquake prediction forecast in Northeast India. This is very relevant at present time, and I hope the 2 days program will come with a fruitful result, and we can do better in the area of the earthquake. As we know, earthquake is the natural phenomena. We can't do anything, but climate change is indirectly or directly related to the earthquake. So we have to maintain our environment to reduce the frequency of earthquake or intensity of the earthquake. As little bit knowledge I have, the BIS Bureau of Indian Standard had divided the seismic zone into 4 categories. Zone 1 is not existing here, and this is not vulnerable. If we are talking about vulnerability, the about 59% area of the geographical area of India is the vulnerable to the earthquake. And we are having, on the basis of YM scale, modified Mercalli scale, if I am not forgetting. 4 categories are there. Zone 2 with 6 or less than 6 on the scale, and about 41% of area in 100 scale. This is coming under the level 2. And the zone 3, we are having 7 in the scale, above 6 and up to 7, and about 30% area of the India is coming under zone 3. Now zone 4, this is on the scale up to 8, and under this 18% area is falling. And the most risky zone is the zone 5. Under that, we are having 11% of the geographical area of the India, and on the YM scale, the value is 9 or more. So this zone is very sensitive, and our entire northeast is falling under this zone, including the Andaman and Nicobar, Jammu and Kashmir, some part of the Uttarakhand, some part of the Gujarat and North Bihar. So I hope prediction of the earthquake, this is rather difficult and very challenging. I hope this program will give a needful dimension or a new dimension in this direction. And I wish a grand success of this event. Thank you very much. Jai Hind.
Thank you for sharing with us your valuable words. Now I request Professor B.P. Sati, convener CDM, for giving a brief introduction about the seminar.
This will be like this only?
Yeah.
Yes, sir. Or I have to do no. Achha. Okay. So thank you very much for calling me this, for to give introduction of this theme of the national seminar. Very good morning to all of you. Honorable chief guest of this national seminar, Honorable Vice Chancellor of Mizoram University, Professor Prabhakar Rath ji, Chairman of this event. How to use? Like this only? I have to keep it like this? Okay. So, Chairman of this event, Dean School of Earth Sciences and Natural Resources Management, Professor V.P. Misra ji. Guest of honor, Sri Anmol Srivastav ji, Additional Secretary to the Government of Mizoram for Disaster Management and Rehabilitation. Professor Kayal, keynote addressee, and galaxies of the invitees and scholars coming over here, our colleagues from the university system and from the department, scholars and dear students. As we know that earthquakes are the most disastrous event caused by sudden movement of the earth crust. The history of earthquakes on the earth is terrifying. There have been many such incidences of earthquakes on the earth which shook the whole earth many times. Although there have been many predictions related to disasters, however, there is no earthquake prediction yet. So we have, like geohydrological disasters or other types of disasters, we have many prediction systems, but for the earthquake we don't have any system. Only after earthquake takes place, then we have this Richter scale and we measure the volume on the intensity of this. So we don't have any scale or any prediction for this. Depending on the intensity of the earthquake, the earth is divided into 5 zones, as our dean of the school has already elaborated this nicely. I will not go for in depth of it. Out of which zone 4th and zone 5th are the most dangerous, where this northeast India is also located, or the entire Himalayan belt. These zones are found parallel to the earth's place beneath of the earth. There are many plates, they are moving, converging, diverging, and due to convergence, divergence, there are huge earthquakes, they are taking place. Geology students, they know about this, or geography also. In the recent past, many earthquakes occurred, such as Uttarkasi in 1991, Latur in 1993, Jabalpur in 1997, Chamoli in 1999, Bhuj 2001, Benchuang in China 2008, Pakistan 2013, Kathmandu 2015, and recently Turkey-Syria border earthquake in 2023 in February. That was one of the disasters. These earthquakes were greater than 7 magnitudes. It is very high, and which caused huge loss of life and property. So I will just give you some very specific data of Himalaya in general and Central Himalaya in particular, that we are observing the tremors that are taking place in the Central Himalaya. The Himalaya is the most earthquake affected mountain in the world. We know that. It is originating from the collision of 2 plates, the Eurasia plate in the north and the India plate in the south. It is the youngest and the tallest mountain system in the world, which is still shifting to the north and uplifting vertically. So the characteristics of the Himalaya, and one of the reasons that Himalaya is highly vulnerable to the earthquake, Himalaya is shifting towards China with some rate, 0.2 millimeter every year, and also it is uplifting. And due to the upliftment of the Himalaya, we know that the height of Everest has increased 0.5 meter recently. The China has measured this one. So because it is uplifting and it is shifting to the north, that is one of the biggest cause for this earthquake. 4 major earthquakes were recorded in the Himalayan region over the past 150 years, including the tremors in Shillong, 1897, Kangra in Himachal Pradesh, 1905, Bihar, Nepal earthquake was in 1934, and Assam in 1950. The biggest one occurred in Assam in 1950 was with the magnitude of 8.7, so horrible. The Indian Central Himalayan region, which is also known as the Uttarakhand Himalaya, falls under earthquake zone 4th and 5th. It has already received many earthquakes in the past, along which the Kumaon earthquake of 1720 and Garhwal earthquake of 1803 were prominent. These earthquakes had 7 and above intensity on the Richter scale. Further, the 2 earthquakes of 1991 and 1999 were devastating, which killed hundreds of people and damaged huge properties. This region is traversed by the major Himalayan tectonic discontinuities, that is the Himalayan frontal fault and the main boundary thrust and the main thrust, central thrust. So there are the main boundary thrust and the frontal fault and also the main boundary. So they are all very vulnerable to occurring of the earthquake hazards. Even the earthquakes that occur in Pakistan, Afghanistan, Tajikistan and Nepal severely affect the central Himalaya. Events from this fact was noticed in 21st March 2023, recently in March 21st. So there was an earthquake epicenter in Afghanistan and the whole North India was shaken, including Dehradun and Delhi. At 10 p.m. it was night time and the magnitude was 6.6 magnitude. So in the Hindu Kush Himalayan region that has taken place and it has shaken the entire northern India. The recent this trend of earthquake is increasing and the intensity is low. So one of the Himalayan region, one of the recent trend is that the earthquake tremors are increasing but intensity is low. Between 1803 and 1991, the average magnitude of earthquake was 7.5 and frequency was 9 only during this time. On the other hand, between 1909, 91 and 2011, the average magnitude of earthquake was 4, while frequency was 56, meaning 2.5 times per year. So what is doing nowadays that frequency of earthquake is increasing, intensity is getting low in terms of the Himalayan region. But earlier frequency was low and intensity was very high. So that is one observation. In the last 6 months between October 8, 2022 to March 8, 2023, there were 12 earthquakes of light tremors occurred in the Himalayan region. You know that every time coming. But intensity was very low. It further shows that Uttarkasi, Chamoli and Pithoragarh are the 3 districts in the central Himalaya that are most likely to have intensive earthquake, and this is also followed by the Don Valley. These seismic incidents lead to the development of 2 ideas have come out of this, what is going on in terms of the seismic events. The first idea is that the future earthquake hazards will be less of a threat as long as the stored stress beneath the earth is continuously releasing by average intensity tremors. Because tremors are always releasing from the earth surface in terms of 4 intensity, 5 intensity. So some seismologists have the ideology that this will lead to less intensity earthquake. The Turkey Syria earthquakes has different story because there was no stress coming from time to time. So stress were accommodating in that area, Syria, Turkey border area. And after 100 years, then this stress was immediately outburst, and this was 7.8 magnitude earthquake on February 6, 2023, and 45,000 people they died, and many people they injured in that incident. The second idea suggests that the main boundary thrust and the main central thrust are constantly building up stress in the central Himalaya, which poses a risk to the possibility of big earthquakes in the central Himalaya. Light tremors caused by tension won't have the impact on the increased likelihood of the earthquake. So other ideology is that even there is, although there is lots of stress coming out in monthly or after some months, but it will not have some huge impact on that the likelihood of the big earthquake in that Himalayan region. A report from the National Geophysical Research Institute said that the region referred to as the seismic gap between the Himachal and the western part of Nepal, including Uttarakhand, is prone to earthquakes that might occur at any time. Recently there was a news and people are afraid about all these things. The report also noted that Uttarakhand is equipped with a strong network of 18 seismograph stations to monitor ground motions of the earth. So there are many instruments. They are monitoring whether the plate, the southern plate is shifting to north or not. So earth surface comprises various plates that are constantly in motion. In India, the Indian plate is moving about 5 centimeter per year, leading to accumulation of stress along the Himalaya, increasing the possibility of greater earthquake, the report stated. I have something more to talk, and because there are lots of other things to be gone, so I will not take much time. So, earthquakes are devastating natural disasters that cannot be controlled. However, vulnerability and risk of the earthquake can be reduced. So that we are talking, as our dean also told, that because it is natural phenomenon, but the risk and that vulnerability can be reduced. The damage caused by earthquake is mainly due to the collapse of the building and slope failure. So in earthquake, people are killed because due to the slope failure and the building collapsed. If earthquake resist building are constructed on the buildings construction constructed, and the building construction can be avoided along the slopes like ice wall. No? So we have to avoid all these slopy area which are very fragile for construction of building, and we have to construct building according to the, you know, that the earthquake resist building, the damage can be reduced. So construction of multi-story building can be avoided in earthquake prone areas such as zone 4th and 5th, as they invite massive disasters. And it is said that it also, I have published one paper and I wrote that one quotation, that it is not the earthquake who kills the people. It is an unexperienced contractor who constructs the building. So if building is not constructed well, it is not earthquake resist, people will be killed inside. Because earthquake never kill the people. Because we have houses in a very slope area which are very, you know, that prone to the earthquake, and we have building also. So it is not earthquake who kills the people, but it is an unexperienced contractor who constructs the building. And we have the system. So now another one small paragraph, I will just talk about this. So tsunamis are different. Earthquake, though you can escape, but from tsunami you are not escape. Tsunami is a, you know, a form of earthquake which takes place in the ocean. And ocean means when it is taking place, the water is rising more than 100 meters. So you cannot escape. There is no place you can escape from the tsunami or from the water. So that there is another suggestion that the earthquake prone areas where tsunami is occurring, we have to avoid the construction along the coastal regions. Those are most vulnerable. And in 2004, there was a tsunami in Indonesia, and the waves came to the India, in even Kerala, and many people died during that time also. And tsunami in 2008 in Japan also, it has damaged lots of things. So our point is that prediction, in terms of prediction of earthquake, it is not possible. We don't have any instrument, but then we can escape ourselves through construction of building, and we have to escape ourselves to avoid ourselves to construct the building in the fragile slope. With this, I stop here, and thank you very much, all of you, for listening me.
Thank you so much, sir, for your for introducing us to the seminar in such an inspiring and beautiful way. Now I request Dr. Laldin Puya, Organizing Secretary, to deliver a brief report and felicitate our honorable members.
A very good morning, all of you, especially that our respected chief guest and guest of honor, our dean, our chairman in the organizing committee, and our convener, and our distinguished invited speaker, Professor J.R. Kayal, Dr. Saitlunga, and our professors, all our colleagues, my colleagues, and research scholars and students, all friends. This is a brief report about this 2 days national seminar. We will have 4 technical sessions. We will receive 61 registration from faculties, scholars, and students. Students including not only master degree holders and also from BSc students from Zurich College, geologist department. So you are very lucky to have such a wonderful mixed participants today. You will receive 14 abstract, then all are accepted for presentation. Tomorrow will be presentation, oral presentation for those accepted papers. And today we'll have a earthquake lecture series from Professor J.R. Kayal. So that will be started out just after this inaugural session. So then I'd like to introduce or invite the speaker. First, please, Professor J.R. Kayal, stand at our place, respective place. Please stand. Okay, that's enough. Okay, thank you. He's a well-known seismologist all over the globe. So he's now serving many years in Geological Survey of India. Now he is adjunct professor and emeritus scientist even in the country and even in the abroad also. He's a well-known seismologist. So he published a good numbers of papers, more than 150 research paper, and also published many books. That's one famous book he published is Micro-Earthquake Seismology and Seismotectonics of South Asia. Even from the bachelor, even up to expert level, so you refers mostly his book. That's a very reference book, a very good book. Then another one, you have to invite the speaker. Another one is Dr. Sait Luanga. Please stand up. Okay, thank you, sir, for accepting us our invitation. So he is now head of department geology, Pacheco University College. He is now only one seismologist now staying in Mizoram. So you are very lucky to have such a wonderful speaker today and tomorrow. So Dr. Sait Luanga will deliver a keynote address on tomorrow, just before research presentations. So now this token of gift, token of facilitations. So I would like to request our respected chairman, our dean sir, and our convener to give our guest of honor and chief guest. So first chief guest. Oh, okay, come. Okay, just. Sorry. So, chief guest, please. Okay, thank you all.
Thank you, sir. Now I request the chief guest of the event, Professor Prabhakar Rath, Vice Chancellor, Mizoram University, to share his thought of wisdom. Okay.
Well, a very good morning to all of you. This is a wonderful topic on disaster management. At the outset, I would like to express my thanks and gratitude to the Center of Disaster Management for organizing such a very good and very emerging relevant topic on disaster management. Professor Misra, Dean of the School, Amol Srivastavji, Additional Secretary, Government of Mizoram, who is dealing with disaster management activities, a very right person for this seminar, and Professor Sati, who is in charge of disaster management center, Dr. Poya, organizing secretary, invited guests, participants, students and scholars. So, hello. Keep quiet. So, it's really a very interesting, not only interesting, it's a topic which everybody is so careful, so much of panic. We know as a common man, there are two types of disasters. One is man-made, another is natural. But in many occasions, and quite practical also, that the natural disasters supersede the man-made disasters. Man-made can be avoided. There are many preventive ways, prevention and cure, both remedial. But natural is natural. This is God's gift or God's, we don't say blessing, but it is what beyond the human control. That is why the topic you have selected is earthquake, prevention of earthquake. Being here in many years, many years, I have never come across very serious type of earthquake either Mizoram or nearby. But it's very common, loss of, thousands and lakhs of lives, never to India, maybe Nepal, China and Indo-Pakistan border. So, I have never seen a very serious type of earthquake being here for a long time, but there are other disasters like serious rainfall, heavy rainfall. Heavy rainfall leads to landsliding. Landsliding leads to loss of life. That is also disaster. That's also disaster. And when many times I spent my life or some assignment in most advanced countries in the world, there is a forecast. Today at 3 p.m. there will be rain, snowfall, heavy rain in advanced countries. Can you say in Mizoram today 4 p.m. there will be rain positively? No. In India also that type of technology, that type of, yes, the meteorological department will say that, that it is expected within 24 hours, after 3 days, maybe certain areas of northern India, certain areas of southern India, that type of general type of things. And because of the advanced technology, specialization, expertise, so till today we are unable to say that today at 3 p.m. there will be rain, or late night at 12:30 there is a possibility of earthquake, but which is certain, guaranteed, prediction is 100% true in most of the advanced countries, because I am a witness. When I was staying 7 months in United States, they will forecast today at 3 p.m. there will be snowfall, there will be little rain, there will be heavy rain, there will be foggy weather, because of the advanced technology that they use. So, such type of things, predictions, accurate predictions, there can be general predictions. This is very much required for human life. Everything is concerned to this precious human life. Well, some papers are there, and many of you may be knowing that I do not know what type of technology and predictions that the government of Odisha did maybe 10 years back, 7 years back, to prevent a very serious nature of cyclone, tsunami, or very serious nature, and the government, that government was well recognized nationally and internationally because they could be able to prevent thousands and thousands, lakhs of people human life. A great honor, a great recognition to that government. So, if we can think of, we are here a generation which is quite dedicated to education and research, students, research scholars, faculty members. We are the people who are concerned with disasters. It is not only earthquake, there is flood, there is famine, there is poverty, there are different types of disasters, air pollution, water pollution, everything causing loss of human lives. How can we prevent such type of disasters? Earthquake is only one. So, therefore, it is our duty, sincere duty, and particularly the youngsters and researchers and faculty members to think of that why India is lagging much behind that. I am not a person of the same subject, but I am concerned with disasters and I am concerned with loss of human lives, which pains. That is why we have to think of what type of advanced technologies, tools, techniques that we can use so that we can have an accurate prediction of all these disasters to prevent human life. With these words, thank you very much for giving me an opportunity to be here this morning. Thank you very much.
Thank you so much, sir. Thank you so much, sir, for your inspiring words. Now I request our guest of honor, Mr. Amol Srivastav, IAS, Additional Secretary, Disaster Management and Rehabilitation, Government of Mizoram, to share his thought to us.
Thank you. Am I audible? Yes, sir. Okay, so thank you. So, Honorable Chief Guest, respected Vice Chancellor of MZU, Professor Prabhakar Rath, Chairman for the event, Professor B.P. Mishra, Dean, School of Earth Sciences, our guest invitee keynote speaker, Professor J.R. Kayal, Dr. Zonun Sanga, Dr. Saitlo Anga, Dr. Din Puya. Thank you so much for calling me here, and I'm very happy and delighted to be a part of this August gathering. But the organizers have put me in a very difficult situation. Right before me, three our Vice Chancellor, sir, and the two Dean and such senior professors have spoken, and right after me, you have the keynote address. So I don't know what new thing or what additional thing I can bring to the table. But given this responsibility, I'll try to do justice. So I got to know about this seminar some time back, and I was very interested and very happy to know that such seminars are being conducted, especially in Mizoram, which lies in zone 5 of our seismic zones, and almost 3-4 months we get to face a minor earthquake. We are blessed that nothing serious has happened, but the frequency of earthquakes that we are getting is completely putting us on risk. So now, as our head of department, Professor Sati, mentioned, and our Vice Chancellor, sir, mentioned about earthquake. So it is, the division is clear that disasters are man-made or natural. But it is difficult to determine if earthquake is a natural disaster or a man-made disaster, in my opinion, because as a geographical phenomena, it's a natural phenomena, but the disaster part of it comes through man-made activities, the incessant, unauthorized constructions, poor quality of construction, poor preparedness abilities of our people, lack of training, lack of sensitization, and delay in response mechanism makes a geographical phenomena into a disaster. As rightly pointed out, in Odisha and on our east coast through our cyclone mitigation program, as well as the tsunami warning programs of the inquest, we are able to get lot of information about upcoming cyclones as well as tsunamis, so that we are well prepared and we keep the administrative actions are almost ready and very prompt to take the people on the safer side, and all those structural and non-structural requirements to ensure that minimum damage is taken, they are ensured. But on the contrary, earthquake is not predictable. Though some research is still going on earthquake precursors, but till now we have not been able to achieve a very specific and a very reliable equipment or a mechanism to predict earthquakes. So this reminds me of the Turkey earthquake, which shook the country on in February this year. The earthquake was 7.8 magnitude, which was the strongest in last 100 years. And almost 45,000 people died. And this reminds me of two more earthquakes in 2010 in Haiti and in Chile. So in Haiti, the magnitude of earthquake was 7.8 and 3 million people died because they were not prepared. On the contrary, in Chile, in the same year, there was a earthquake of magnitude of 8.8, but only 525 casualties were reported. So this shows if the country and the society is well prepared, then we can reduce our casualties and we can reduce the impact on livelihoods, our livestock, our infrastructure, and almost everything through better preparedness. Now again, Mizoram, as I told, it's on zone 5, and such seminars are being conducted. And when I see the list of the papers and the presentations, most of them are quite relevant to Mizoram, and the study has been conducted in Mizoram, Indo-Burma region, Champhai, structural abilities, as well as soil testing, climate-induced disaster, then vulnerability of planned cities. So all these things are very relevant to our state, and definitely we have experts from across the country. So we'll be able to help and give a better scientific as well as educational inputs to the concerned administrative authorities. Now, today's seminar and the 2-day seminar where we are going to dwell upon all these things is a very important aspect for disaster risk reduction in our country, and all the experts present here and the students who are going to pursue their career in this field are going to be the real saviors of our society in the coming days. So from this platform and as an administrator, I just request that whatever things are being discussed here and whatever relevant insights and outputs are achieved, please share those outcomes with the government so that they can be implemented on the ground and they can be taken up with the right authorities. So I feel that all the scientific discussions as well as the research that is being conducted on such issues, unless it is executed on the ground or its applicability is tested on the ground with the relevant authorities, we are not doing full justice. And at the same time, whatever executive action or administrative policies the government is making, if it is not backed by scientific evidence and not backed by the scientific understanding, they are bound to fail. So a proper coordination and a multi-sectoral approach is required between the government and the academicians, with a range of organizations that exist: Geological Survey of India, Bureau of Indian Standards. So many universities are doing research on these subjects. So we all have to come together so that whatever we feel is the need of the hour is actually implemented. So with that, I'll thank to the organizers for calling me here. And I am looking forward to listen to our keynote speaker, Professor J.R. Kayal. It will be a good learning experience for me and for all of us. And I give all my best wishes to the faculties and the students who are sitting here. It's a very relevant subject, and please pay attention. I see some of you are sleeping. Now it's a wake-up. The Turkey earthquake was a wake-up call, so I think I should give a wake-up call right now, so that the 2 days that we are going to dwell upon, we use the best of the time, because so many experts at the same location, it's very difficult to gather. So I'll just request you to make and utilize the best of the opportunities that you have been given by Mizoram universities and bring the best of it. Thank you.
Thank you so much, sir, for your inspiring words. Now I request Professor J.R. Kayal, Director General JSI, for keynote address.
Put it in the pocket. Very good morning to all of you. Chairman of today's event, Professor V.P. Mishra, Chief Guest, Professor Rath, Vice Chancellor, Guest of Honor, Mr. Amal Srivastava from DMR, and Convener in charge, Convener, Professor P.P. Sati.
Hello.
And Convener, Professor Puya, and all of you, Professor Sai here. It's my great pleasure having invited to be with you in this morning. At the outset, I convey my sincere thanks and gratitude to the organizers for inviting me. Today morning, Professor Puya was telling this is a burning topic. Yes, and as Professor Mr. Srivastava said, that the Turkey earthquake was the wake-up call. Very nicely said. And on the burning topic, you have put a old seismologist to burn on the fire to say something on the earthquake prediction and forecast. I think Chief Guest has clarified what does it mean by forecast and prediction. Please. And as of today, the seismologist, let me confess before you burn me on this fire, the seismologist cannot predict earthquake with specific time, space, and magnitude. To some extent, it is possible to forecast the vulnerable areas or approximately, in near future, maybe few years to tens of years. So that has no practical utility actually. So the way, we cannot stop earthquakes because earth is a dynamic body. We can try to understand the earthquakes by monitoring earthquakes, by imaging the earth structure below the study area. Like the doctors, they examine the human body but cannot predict when you will have the last breath. They have the body, very under their much control and lot of examination, lot of stress they can make, but even then they can't predict our last breath, when we are going to have the last breath. So seismologists can monitor earthquakes, can understand the earthquake processes, but cannot predict when and where and what magnitude is going to occur. So that part is very real. That is the reality of life. But one good point Mr. Srivastava has raised as a disaster management authorities, point of view, that you see the Haiti earthquake and the Mexico earthquake, the casualties, how they reduced the casualties. 50 years back, the advanced countries and developing countries had almost, a similar level of casualties due to large and great earthquakes. But today, advanced countries has reduced the casualties almost to nil, say like in Japan or in California. They have reduced the casualties to nil. But in developing countries, we are enhancing the vulnerability of casualties. Say, in 1905, the Kangra earthquake in Himalaya caused some 19,000 casualties. If such earthquake occurred in Kangra today, it will cause 19 lakh people, dead. So that's the reality. We have not learned, we have not taken lessons from earthquakes, what the advanced country has taken, and we are yet not prepared or aware about the consequences of the earthquake. So I think the young generation has to take this message, to build up a resilient society. That Mr. Srivastava has already explained. Now let me share some experiences of earthquake prediction in India and outside India. We are, in a sense, much young science. Seismology is a much young science compared to geology or physics or other subjects. The instrumental seismology started sometime in early 1900s, 20th century. So hardly 120 years we are able to record earthquakes, and that too digital instruments has come only in late 90s. So our data on earthquakes is much meager in that way. Hardly 100, 120 years of data, earthquake data. But with the advancement of science and technology, seismologists tried to monitor precursors, whether there is any change in the Earth's body, like human body. Doctors, take the ECG, take the X-ray, so many things. So we try to examine some, make some test of the study area, whether any physical parameter changes before a large earthquake. That is called precursor. So that study started all over the world. In the peak time, it was, in 70s, 80s, it was peak time. All seismologists, were in this game to monitor precursors to predict earthquake. But it was not really. It was good to publish papers and books, but of no practical use actually. We cannot, from that precursor, you cannot say when and where and what magnitude earthquake is going to happen. And sometimes there is no precursor. I'll share a story with you. In 1970, you all know that China is very prone for earthquakes. In 1975, the China is they still believe that they will predict earthquake. Till the other day in the conference, they are, determined to predict earthquakes. So in 1975, China works like a team. Even the villagers work like a team for precursor, measurements. Means a villager will tell if there is any change, any oil water or whatever, spring discharge, all this information will go to the local office, say BDO office or whatever. And the scientists are measuring the physical properties like resistivity, gravity, so many things are there, geochemical, geophysical. lot of measurements can be made. I will take up that, in my technical session, what we can do and what we cannot do. So there were some precursors for the 1975 Haicheng earthquake in China. But unlike India, no scientist or no, even in our country, astrologer, predict earthquakes. So no scientist or no person is authorized to predict earthquake. So all the scientific information, even the village information from the local offices, go to the earthquake prediction authority like that. Some central body is there. So they were at a loss what to do. There is really some report of some abnormal physical properties of the earth and geological, seismological earthquake, seismicity rates changes, gravity changes, magnetic value changes, resistivity changes. So there are reports, but they did not or could not predict the earthquake. What they did, suddenly one fine morning, they found that all the insects and rats and snakes all are abnormally on the road in the whole Haicheng city. Then the authority announced, you evacuate your houses immediately. So all people, they evacuated the houses, they are putting on the tents or whatever in the open ground, and they saved lives. Some 3 million lives were saved, but the whole city was destroyed. So message is here that by predicting earthquakes, that too with animal behavior, it was the only successful prediction. The city could not be saved. In the same country, in 1976, the Tangshan earthquake, similar magnitude. I'll show you in the technical session. About 500 kilometers away or so. The Tangshan city, some 3 million people, and whole city was destroyed by similar magnitude earthquake by 7.6. No precursor, no animal behavior. The whole city was destroyed and people were killed. So I really appreciate Mr. Srivastava's last comment that we have to be prepared and aware to make a resilient, earthquake resilient society. What Japan has today done, what New Zealand has done, what California has done. We cannot stop earthquake. It's a dynamic process of the earth. It's a natural process of the earth. We cannot stop the earthquake, but we can save lives. So that is the, I think, most important message. And how to do that? Though we have a seismic zoning map, already it was told to you, and you might have also know about it. Now within this zone, there could be some spots which will be much vulnerable for total damage, and some spots are not. That we have observed in a Jabalpur earthquake. It was hardly 6.0 magnitude earthquake, and within the maximum intensity zone, I think there is a magnitude and intensity as two different terms. I will explain that in the technical session. So within the same intensity zone, one building is totally collapsed, and about 100 meters away another building is standing, more or less same construction, same material. So that we call site response, site amplification. Some sites are very much vulnerable for damages, means it's highly amplified by the seismic waves, like loose sediments. So what we do, seismologists, what we do, we study many geological, geophysical parameters and seismological parameters, including the site amplification factors, the crustal thickness, the alluvium thickness, all these things, parameters are studied, and we bring out a micro-seismic hazard microgeneration map. I think all disaster management authority, they have access to this map, or they have this map from the GSI or from MOES. For all the cities in the country, capital cities in the country, The seismic microregional map, it was a mission in in early 2000, it started. First microregional map we did for the Jabalpur area. Then for the Guwahati area, I will elaborate it in the technical session. So the seismic microregional map should be taken care of for any building, and disaster management people also can take care of that. After the seismic hazard microregional, we bring out the seismic risk area. Risk area means any place can be seismically hazard. Say in seismically hazard, say crustal deformation or fracture, all these things, or liquefaction may happen in a desert, but there is no vulnerability, there is no casualties, but the whole area is, there is no population, so there is no much risk. Seismically hazardous area, but not seismically risk. So you must understand what is seismic, what is hazard and what is risk. Risk is seismic hazard into multiplied by the vulnerability, how many people are there living there. So for that we have made a detailed study in Guwahati city when I was in GSI in early 2000. So these are the maps which gives you guidelines for, means what is the frequency, at what frequency that ground particular spot will be amplified. That frequency has to be taken care of by the engineers to build the structure, to build the house. And risk map, I think most useful for the disaster management authority people, because they can immediately know what are the spots they have to send the support or the help. So these are the maps which can be produced by the seismologist for the preparedness and for the awareness to save casualties like Japan and California and New Zealand. There was also a point about tsunami. If I have time, another maybe 1 minute or 2 minutes I will take. Tsunami is the earthquake effect. When an earthquake occurs in the ocean floor, a high magnitude of the order of great earthquake, 8 and above, or sometimes 7.5, 7.7 earthquake, large earthquakes and above earthquakes. When it occurs by a particular mechanism, then by thrust mechanism, if you understand thrust mechanism, I will explain that. Then that earthquake in the ocean floor, if it is shallow, that causes sea waves to propagate and coastal areas are flooded. So in Japan, I will just share you, in Japan that 9 magnitude earthquake, 9.2 or 9.1 magnitude earthquakes, the 2011 Tohoku earthquake, the people are not killed by the earthquake because Japan has made a resilient, earthquake resilient society. After the Kobe earthquake, all the old buildings in Japan are retrofitted, and all the new buildings is mandatory to make earthquake resistant building. I will show you that, how they make it. So Japan has made the country almost nil casualties because of earthquake. I happened to be in Japan as a visiting professor in 2007. I was in the guest house, and in the early morning, maybe at 3 o'clock or 4 o'clock in the early morning, my bed was shaking, and immediately I could understand some earthquake has occurred. And I was not panicked. I didn't run out from my room, and I was rather, you will laugh, I was rather enjoying that vibration, that swing of the bed. Because I am in Japan, the building will never collapse and I will not be killed. So I was not panicked, I was sleeping, or rather enjoying that swing. And in the morning, in the TV, in the breakfast time, I found there was a 7.6 earthquake in the ocean, and no building or no casualties, not nil, nothing happened. All are earthquake resilient buildings. So that is the story for Japan. But what happened to 2011 earthquake? They expected from the historical data that maximum magnitude 8.5 earthquake can occur. So accordingly they made the wall for the tsunami, to protect the tsunami from the nuclear power plant. So their wall was of the order of some 8 to 10 I think meter or feet, I forgot, maybe feet, 8 to 10 feet high, because that is the maximum tsunami height they can expect for the any tsunami in the Japan Sea, in that Pacific Ocean, that Japan coastal area. But the earthquake was mega earthquake, 9.1, and I know, the earthquake of magnitude 8 and 9, there is a hell and heaven difference. It goes in power law. The earthquake of magnitude 9 is equivalent to of 30 earthquakes of magnitude 8 at a time. It is in power law. You know what is 8, Assam earthquake and Shillong earthquake. So 9 means all earthquakes with magnitude 1 unit increase, the power goes 30 to 34 times. So a 9 earthquake of equivalent to a 34 magnitude 8 earthquakes at a time in Japan Trench. Even that type of earthquake did not kill any people, any person due to building collapse. It was, the tsunami was of the order of something like 20 feet high. So that was, beyond their control. So that was their, beyond the anticipation. Anyway, I think I have taken much time, so I stop it here. I will share more experience and my little knowledge with you. That is what is my great pleasure to come here. Thank you so much for your listening, and I think we have a big day today. Thank you all. Can you open it up?
Thank you so much, sir, for your valuable words. Now I request Dr. R. Zonan Sangha, co-convener of the event, to deliver vote of thanks.
Okay, not a problem. I can manage. Well, Chairman has left. I would like to thank our host and anchor, Ankita Mishra, who is my PhD scholar. She will be very beautiful, Ankita. And respected chief guest, Professor Prabhakar Rath, Honorable Vice Chancellor of MZU. He too has left, for he has another meeting scheduled at around 11:30. I heard from some sources. Respected guest of honor, Mr. Amol Srivastava, IAS, Additional Secretary, Disaster Management and Rehabilitation, Government of Mizoram. Respected keynote speaker, Professor J.R. Kayal, and former Deputy Director General of the GSI. Respected convener of the Center for Disaster Management, Professor V.P. Sati. Respected organizing secretary of this seminar, Dr. Laldin Puya. Distinguished guest and invited teaching faculty. Let me start from here. Dr. Jimmy, Dr. Sai Tuanga, who has been my teacher right from my college days, and Professor K.S. Rao, and Professor U.B. Rao, my supervisor, my PhD supervisor, Dr. Bodati Biswas, Dr. Bobby, Dr. Kavita, of course, out there, my beloved colleague, Dr. V. Zeta. Many of you are going to chair and moderate technical sessions today and tomorrow, and all the dynamic PhD scholars are brilliant students of the Department of Geography and Resource Management, and are brilliant students of disaster management, and ladies and gentlemen who are with us here today. At the outset, I would like to thank you all for being with us on this auspicious day. And it gives me an immense pleasure to have this opportunity to propose this vote of thanks amidst this gathering of the intellectual circle. I am happy that we have come to this very day which we all have been eagerly awaiting since the second half of February this year. Before coming into details, I shall have my words started with a very short history of this seminar. I shall make it very short. Honestly, we are not eligible to have this seminar organized, honestly. We are not supposed to come here and gather around today. You know why? Because we were late to apply for this seminar. Students of Geography and Resource Management, as well as students of Center for Disaster Management, you all must be very well aware that Dr. Madina and I were taking you to Sikkim, Gangtok, and Darjeeling and other parts of the country for your CSST, spending the whole first 2 weeks of February. The whole first 2 weeks of February, we were out of station on our, we were on our study tour. And then, you all know that very well. And against that study tour schedule, a notification was issued by the concerned authority that the last day for applying for this seminar was 11th February, which means that we were late to write the application and we were late as well to submit the application to organize this seminar. However, no sooner did we reach the state of Mizoram and the campus, our kind-hearted Honorable Vice Chancellor, Professor Rat, informed us through Professor V.P. Sati to meet him at his office, and the three amigos, Professor Sati, Dr. Madina, and I, we climbed up the hill and entered the Vice Chancellor's chamber, where we had a very, very short meeting. And on reaching the Vice Chancellor's chamber, we started narrating the compulsions we had for failure of submission of the application. And then, fortunately, with cool and a calm voice, our Vice Chancellor says, go back to your department, prepare the budget, and send me the application within a couple of days. Maybe within 2 days. And we did. Our Dean of School helped us a lot, and we know the result today. And we are now organizing this seminar. I think we really need to thank our Honorable Vice Chancellor, our Dean, and the convener as well. And once we had that green signal and approval, I'm going to make it very, very short, do not worry. Once we had that green signal and approval from the concerned authority, we wanted to make this seminar great and fruitful. And a seminar, to make it great and fruitful, requires eminent citizen as resource person who are well educated, having vast knowledge, and most of all, a very, very committed person. That is how we should measure how successful and how fruitful a seminar is. So we sent a very humble request and invitation to Professor J.R. Kayal to be our keynote speaker and to be our resource person, and he accepted it. So thank you. And thanks to our invited speaker, Professor Kayal. Then things went well. So far, so good. But my dear students, I'm not going to address the teachers. My dear students, please remember that in every walk of life, we human beings are created to meet with obstacles and hurdles. You got my point? To make ourselves more stronger. So the budget for this seminar was just an estimate. And lately it was realized that the budget might be insufficient to meet all the logistics. So we were worried. Dr. Madina and I, we were a bit worried. To be honest, we, the two disaster managers, were possibly in a disastrous situation. And who knows, we might need rehabilitation as well after this. Then came the state government, Department of Disaster Management and Rehabilitation. Mr. Amo Sevastava and his team gave us money through sponsorship. Ladies and gentlemen, let's give them a big hand. Well, let me go ahead. Another point is, since the inception and the creation of this Center for Disaster Management, we have been receiving technical as well as non-technical support from the Department of Geography and Resource Management in terms of academic as well as administrative services. They have given us guidance just like a father does to his son, and have given us care and motivations just like a mother feeds her daughter. Thank you, Daddy. Thank you, Mommy. Geography and Resource Management Department. And to all the invited chairpersons and moderators, we thank you all for joining us today. We appreciate the precious time you are willing to give to us. And to all the registered participants who are to present papers and who are here today, we admire the thirst you have had for sharing us your valuable knowledge as well as for gaining more knowledge. And to all our beloved PhD scholars, MSc students, you really look very beautiful today. It has been your efforts and hard work which bring us to this wonderful day today. To conclude, I would like to point out the services rendered to us by the non-teaching staff of the department as well as the Dean's office, allotment of this Dean's conference hall, the decorations, the arrangements. To me, it feels like a Christmas in the month of April. And lastly, kudos to my colleague, Dr. Madina, the convener and the organizing secretary of this seminar. I must say that I have never ever met a more dynamic person than this gentleman. He is always ahead of me and I'm just following his gentle reminder each and every single day. He would send me a reminder, we have to do this, we have to do this. So I really appreciate, I'm really happy to have a colleague like him. Thank you all.
Thank you so much, sir, for your valuable words. After this, first technical sessions will start just after group photo. Okay. Thank you.
Now, technical session starts. Now I request Professor J.R. Kayal to deliver his speech on earthquake prediction, forecast, earthquake signs, sign zones, and bridges.
Pointer.
Sir, you can.
Yes, you can come as close as possible. If you can read from the back bench, can you read from the back bench? Okay, let me start. Yes, I think this is better, yes. Then I think you can take it out or what?
No, that's a different channel, no? This is for the video.
Okay. Good afternoon to you all again. And I was given a topic by Professor that I have to speak on earthquake prediction and forecast. And he has given me 4 slots, 4 lectures, series of lectures under this topic. Then I decided to understand the earthquake science. What is earthquake? What are its generating process? Then source zones. What are the most vulnerable source zones? In Northeast India in particular. I am not going to speak on the whole country. This is a special series of lectures on Northeast India seismicity. Then precursors. Whatever you could understand on this topic in this part of the country, in any year, particularly this is the field laboratory to understand earthquakes. Actually, I started my seismology career from here in India. I did my PhD abroad in New Zealand on seismology. But coming back to GSI back home, we started the instrumental seismology in the GSI in 1980s. That was the first beginning of instrumental seismology in the GSI. Before that, there was permanent observatories run by IMD. But mobile network was started by GSI in 80s after I came back from New Zealand. So along with the monitoring of microseismicity, we tried to also understand if there is any physical parameter changes of the earth before a large earthquake. So that part also is a very relevant part under this banner of this today's seminar. Then comes, I think, most practical part for the preparedness. To make a earthquake resilient society, I think microjonation is the technique which we should learn and try to make a resilient society through this study. So these are the 4 topics. I will try to, I cannot go very detailed, but I will just touch upon so that you can have a glimpse of the subject, because every topic is it take one semester, you can say. So I will just give you some idea, because some of you from geoscience, maybe some of you from engineering department or some disaster management center. So for all of you, I cannot go into details. It is not a that type of semester class. It will be just a seminar, but I will try to give as much as possible so that you understand. And if there is any doubt, you can ask me anytime. How it goes? Oh, it has come. So part 1 is earthquake science. The basic thing we will understand. Can you? Yeah. Okay, please. Next one. I think this is very, very popular picture. All of you have seen, might have seen this picture. Particularly the geoscience students must have seen this. So this is based on seismicity, how whole Earth's surface can be divided into some major plates. And for the light, I think the upper one, or which one is the indicator? Which one is the indicator? Last one?
Yeah, the lowest one.
Lowest one? Okay, fine. No, it's okay. I can do it. So, based on seismicity and geomorphological evidences, you can see this plate, which is the most burning plate, you can say, the ring of fire. You have all heard about it, the Pacific plate. How it is generating from this mid-oceanic ridge, where the fractured zones is there in the middle of the ocean, and the molten material from the Earth's interior. It's a dynamic process. The Earth is a self-dynamic system. The molten material coming up, it is spreading, again going down, again getting melted, and again coming up. So that is the plate tectonics hypothesis. It's a dynamic process of the Earth's interior. So from the mid-oceanic ridge, the Pacific plate is moving towards this direction and anti-clockwise, you can say, and it is subducting. There is a trench here, Aleutian Trench and Japan Trench, Philippine Trench, Hikurongi-Kermadec Trench, like that. So the plate is moving from both sides, from this ridge, spreading ridge, we call it spreading ridge. The material is moving from both sides, and in this side, this plate is subducting or going, getting consumed along the trenches. And this part, there is no trench, but there is a transform fault, long transform fault, that's San Andreas fault, California San Andreas fault. So along that long fault, these two plates are sliding past each other. So because of this plate interaction, the subduction here, all along this trench zones, and the transcurrent movement over here, the earthquakes are occurring all along these plate boundaries. Similarly, Najaka plate here, this another plate which is spreading from this ridge and going, subducting below the Chile Trench, and lot of earthquakes in this South American plate. And if you come to this part, the Indian plate, they used to call it Indo-Australian plate or Indian plate. This plate is now, this is the Carlsberg Ridge, the mid-oceanic ridge, where from the plate is moving to the north-northeast. And it is the land part of the plate, continental part of the plate, is now on head-on collision with the Eurasian plate. So this is the collision zone, head-on collision, continent-continent collision. And this is and the Indian oceanic part, oceanic plate, is subducting along this trench, this Andaman, Sumatra, Java trench. So lot of earthquakes here. So these two circles are showing that the tsunami-genic earthquake in the ocean, in the trench area, that tsunami-genic earthquakes over here and for our country, and also in here, the Makran trench here, where the Arabian plate is subducting below this Makran trench. So these are the two tsunami-genic area for our this Indian continent, and this whole. Now, of course, they have divided now this as a Indian plate and Australian plate, because there is some ridge here they find with the recent seismicity, but this is broadly one plate they used to name Indo-Australian plate. Now this is the African plate, all this plate, and this is Eurasian plate. So these are the major 6 plates, and there are many micro plates. So these are the major 6 plates which is tectonically active and moving, and because of that tectonic movement and interaction with the other plates, the stress is generated and earthquake is occurring. Can you go next slide, please? This is just to show you the present scenario of the observatories of the country. This happened to be the 125 years of the 1897 earthquake. So we are also making one workshop in Calcutta from our ISM society. And so this is the first earthquake was recorded by instrument. But that time we had no instrument in the country. It was recorded outside India. In 1886, the first instrument was installed in California. And then there are some 10, 15 instruments in those days, analog instruments in early 19th century, rather late 19th century. And India had no instruments that time, no observatory that time. So 1897 earthquake is the first earthquake which gave us the first instrument in India, in Calcutta, in Alipur, because that was the British time. So the instrument was installed in Alipur. That is the first instrument installed in India in 1899. And since then the Kangra earthquake came, another great earthquake in Himalaya, Western Himalaya. Then I think it went up to something like 5 or so, more instruments. Then I think 15 observatories by 19 hit 1930 to 1960. So not much. India was having very poor network since even till 1960. Then after the, particularly after the Kilari earthquake, the whole country was, shaken, the whole world was shaken because such a huge casualty in Kilari in the central part of India, which was supposed to be a stable land. So that earthquake gave a tremendous change in our country to develop the network, and we started the digital network in late 90s actually. So 96 actually we first installed, and 97 the Jabalpur earthquake was the first earthquake recorded by digital instruments, by broadband instruments. So today we have something like 200 total instruments all over the country. It is not much. Some country like Japan may be equivalent to a state of our country, West Bengal state. That country has something like 8,000 broadband instruments. And such a big country, we have only hardly 200 broadband instruments. So we are still, we have to make more instruments. And already, as you know, that our campus here, we have one instrument now, or two instruments in Mizoram from Jorhat, from NIST. So this is how the network is, getting increased, and but still long way to go. Next one, please. Now, little history of earthquake. This was the first, they call it seismoscope, was first developed by Chinese seismologists or Chinese scientists. But this instrument, the scope, the seismoscope, like a round, globe. This instrument was able to record the time, at what time that there are some six or seven, 8 balls, and from the direction, from which direction the shaking is coming, the ball falls down, something like that. So that records the time. So it used to give us the time of the earthquake happening. That was something like some 130 AD or so. So that was the first, seismoscope, not a seismograph, it's called seismoscope. Then the first seismograph was in California, 1887, not even 86. In 86 it was developed. So the first seismograph was installed sometime in 1887. And then, of course, this is the, again, analog system, but this is portable instrument developed in early 70s, 1970s. And these are the sensors. This is a recorder. It is recording by pen and ink. This is recording by on smoke paper. So these are the control panel, and these are the sensor which is put on the ground. So these are the components of the instrument which record the earthquakes. And this is how the the seismometer, vertical or horizontal, they work. This is the just physics principle of that. And these are the records of analog seismogram. This is the how we record the digital system. And this is one magnetic tape seismograph which I use in my study, and also the telemetric means various stations can be, signal can be brought to one central station, and you can have all the stations record. So that also used to have a very good system in Jorhat, but now I think that system is not working anymore. Anyway, so this is magnetic seismograph. This is on a film, developed a film they used to record, and then these are the digital records that we record now. And you can also get a print, or you can on the computer screen we study them. So this is how gradually the seismograph station, seismograph instrument developed to record earthquakes. So it's hardly 120 years history. Next one, please. Now the beauty of digital instruments, just an example I am showing you. With this analog system, analog rocks, you can see such a large earthquake, that is, I think, Alaskan earthquake. Yes, 9.1. There are some 5 mega earthquakes so far happened. One in Aleutian, one in Chile, one in Japan, one in Sumatra. So these are the mega earthquake, means 9 magnitude earthquake, 9 and above. So you can see in those days we had no digital instruments. And one mega earthquake of the order of magnitude 9.1 Alaska earthquake at Alaska Aleutian Trench, I have shown you that Alaska trench. In that trench, normally in the trench where this plate is subducting, there you get great and mega earthquakes. So, can you read this seismogram? So difficult. You know, onset maybe when the first arrival came, I can also cannot see from here. Anyway, that can be read where it started. But then there are so many round, you know, the drum is moving and the pen is moving. So its whole record is jumbled up. But with such record, with such difficult record, where you cannot find out the POA first arrival you may find, but the other phases, there are so many converted phases, so many S phases, so many converted phases. Every wriggle of the seismogram is to be studied by seismologists to understand what has happened below the earth. So this was very difficult seismogram in those days, but with such difficult seismograms, the seismologist has brought out the structure of the earth in those days. And today we have this digital seismogram. This is something like 2 hours record or so, and you can expand it on the computer screen, and you can read very precisely, thousandth of a second also you can read the phases, different phases. So this is how you can see how difficult was this and how now, and whole record is so, and this is, you know, that P wave and there are S wave, this is S wave, there are so many converted phases, means many discontinuity is there, say Moravisic discontinuity or lithosphere and astrosphere, you know, a discontinuity is there. So from those discontinuity, the seismic waves is getting converted. So there are, you know, very complicated things are happening, and those are, everything is getting recorded. And then at last that, you know, surface wave, we call, you might have all read that P wave, S wave and Rayleigh wave and La wave. And these are the Rayleigh wave, is, you know, it is moving through the surface of the earth, very, you know, very low frequency. That also are recorded. First round, second round, third round, like that. So that wave is going and going on the surface. So surface wave is also vulnerable for damage. So this is how we have developed from analog to digital system, and now every transition zone or every discontinuity of the Earth's interior is now understood. And you know, from this figure, there is hardly 5 kilometer difference. That Gutenberg Richter discontinuity, which is at a depth of 2900 kilometer, that was estimated from such type of records in those days. It was actually by Oldham, GSI Director General that time, but he did not publish. Then Gutenberg Richter published that. So it is known as, possibly all geology students knows it, Gutenberg discontinuity. So it is by by their name. So that is 2900 kilometer depth, and now with this system, it has come 5 kilometer difference, means 1995 kilometer depth. So that is the dedication of, you know, those seismologists in those days. Next one, please. Now, these are the recording. You have seen how the earthquakes can be recorded and how, but what we'll do with this recording? Now some PhD students here, they are now studying these records, which is installed in Mizoram University campus. So now, the basic thing is, first thing is that a seismologist has to locate the earthquake. Now, how one can locate the earthquake? Suppose this is your hypocenter. Hypocenter means the focus where the earthquake has originated at a depth. And above that, that point is called epicenter. On the map, the point is called epicenter. At depth, that focus is also called hypocenter or focus. So this is hypocenter, and just project it on the epicenter. And suppose this is your instrument, seismograph. So this distance can be estimated simply from this S minus P time. The P wave has come first because the higher velocity comes at about 6 to 8 kilometer per second velocity, depending on the crust. Crust is about 6.5, and mantle is 8.1. So on that velocity, the P wave first comes, that is recorded. Then S wave comes, that is you have all might have read that Vp by Vs, ratio, velocity ratio is 1.73, means P wave is about 1.75 times more than S wave. So that's the normal average velocity ratio. So S wave velocity is low. So the S wave velocity, and that S wave is coming, with in a what should I say, in a shear, vibration. P wave coming like, just straight is coming up and down. The particle movement is just up and down. But shear wave movement is horizontal to the direction of propagation. P wave motion is along the line of propagation, like this. But S wave is coming like this. Korat, jisko bolte hai. So it is dangerous. S wave, when you feel first earthquake, you will feel some doom, a big sound that P wave has come and hit your house floor, and you get a sound, and that feeling will be just up or down. Your building has gone up, P wave has come like a up motion or down motion. But it is, if the earthquake is, next S wave is coming, say, in 15-20 seconds, if you have time, if you are on the ground floor, you may come out of the house. But if you are in a multi-story building, you cannot come out. So it is not advisable to come out. So P wave does not kill you, the S wave damages and kills you. So if we know this difference of time, we can, and that difference is something like this, about 8 times the S minus P time. Suppose S minus P time is 10 seconds, then this distance, hypercentral distance of your earthquake from this particular observatory is about 80 kilometers. And epicenter is a little less. So you can find out the depth and epicenter distance from trigonometry. So this is how manually they tried to, from different stations, till the other day, when there was no computer, the people used to locate the earthquakes by drawing the arc. And knowing the S minus P time from different stations, they draw the arc, and those arcs, crosses at one place. So that is the epicenter position of that earthquake. Till 1960s or 70s, this practice was done by IMD, till the computer was not there. So this is how the physics of the earth is that if you have P arrival time and S arrival time, and manually they can be plotted, they can be epicenter can be known. But then the computer came, and we started locating earthquakes by computational methods. So I cannot go again. This one slide is maybe it will take someone maybe a few few classes. So I will just give you some idea how manually they used to locate. Now how the computational method can locate the earthquakes. So there is one least square method. Means you all in your higher secondary or so, you have all heard about this regression. So you have S time and P time at different stations. So you are giving this data to the computer to make it a multivariate regression analysis to give you the location of that earthquake and depth of that earthquake. So that is the basic, you can say, method of locating earthquakes. Then comes, but for research type of thing, then you have to do the much precise location, that is, you just know the name, is called joint hypercentral determination. This can, because at different stations depend on different geological formations, so the stations have got some factors, so those factors are taken into account in this method. Then double difference method means you take the S minus P time for every station and do the regression. So these are very high advanced seismology. I am not going to that. Just you know that earthquakes are now precisely located by various methods, computational. And for research purposes, this joint hypercentral method, and also by this seismic tomography method, inversion method. Seismic inversion means, simultaneous inversion means, when you are giving only the P arrival and S arrival data, you are doing the regression, so there is one way. But when and you are giving a velocity model. So based on your velocity model, it is locating. It is not simultaneously, it is not getting you the velocity structure. What is there, whatever you are giving the velocity model, say for below this area, your first layer is some 4 kilometers second layer is 6 kilometers, third layer is 7 kilometers, like that. So that model you are giving, based on your model, based on your data, computer is giving you the best possible location of the earthquake. But in this method, much precise method, you are also trying to image the velocity structure of below your study area. Means you are scanning, like your body is scanned, you have put so many sensors and X-ray is sent to your body and you get X-ray, you scan your body. Similarly, at different stations, seismic rays are coming. So again, by doing inversion, like X-ray, that intensity of X-ray is by inversion technique, they get the image of the body. Similarly, medical tomography. Similarly, we can do the earth structure tomography. We can image the earth structure below your study area by seismic tomography. I think that much is enough, good enough, and it gives better locations and it gives the structure below your study area. Next. Now, these two basic things, particularly for for who are not from geoscience, I think is very much confused, particularly the journalists. They make it a mess sometimes. Nowadays, maybe they are making little mistake, but in those days, in 70s, 80s, they used to call an earthquake of intensity 7.8. It has no meaning. Intensity is defined scale and magnitude is defined scale. So magnitude has got defined scale, and most popular known that these are Richter scale, body of magnitude scale, surface wave magnitude scale. You have heard that MS, surface wave magnitude of that, what we call Assam earthquake 8.7 or Shillong earthquake 8.6 or 8.7, something like that. That is surface wave magnitude. What is surface wave? I have just told you in my previous slide. But nowadays a much mathematical scale has come. We call it moment magnitude. So in this moment magnitude, this scale is much stable. Richter scale is good enough up to magnitude 6, 6.5. But beyond that, it saturates. So there are different scales, and magnitude is also different by different scales. So you will find that 1950 Assam earthquake, MS 8.7, MW 8.4. So common people will confuse what they are talking about. The seismologist is sometimes saying 8.7, sometimes saying 8.4. What is this? The point is the scale is different. And take it from me that MW is much precise scale. Is considered to be much precise scale. Richter also precise is valid, rather it comparable with the MW up to magnitude 6. But beyond magnitude 6, Richter scale gets saturated, so it is underestimated, and MS is overestimated. So MW is nowadays you will find MW. That means moment. It is a mathematical scale. That means moment magnitude is mass stable scale and mass stable magnitude. So I just give you the information that there are various kinds of scales of magnitude, and moment magnitude is nowadays most stable scale, considered to be most stable scale. Then there is duration, signal duration. Then macroseismic from the degree of damage you can just by empirical relation you can find out a magnitude. So this is an example of the Richter magnitude scale, how you get P wave and S wave. You know the distance. If you know the distance, S minus V time, this is the scale. And if you know the maximum amplitude of the S wave or maximum amplitude of the seismogram, from that maximum amplitude you have got a scale, and you cut it here, what is the amplitude, you point out here what is the S minus P time, and join this is the magnitude, Richter scale. It's an empirical monograph, but it works very well. And that is the first scale was designed by Richter in 1935. Because what is the size of the earthquake? The magnitude gives you the size of what was the power of that earthquake, energy of that earthquake. And intensity is what is the degree of damage of that earthquake. Two are two different animals, and they are always mixed up, used to be mixed up. So this is how, as I said, magnitude 8 earthquakes is equivalent to that of one atom bomb of Hiroshima. Means, some 100 atom bombs of Hiroshima. So it is a huge energy. Then comes the intensity scales. Intensity, as I said, it is degree of damage, because one earthquake may cause this building total collapse, and in Guwahati area, that earthquake, say one earthquake occurred just below this building, and it has totally damaged this building. But that vibration or that wave has caused little damage to Jorhat or to Guwahati, some crack or some fault. So the intensity of the earthquake varies from place to place. The magnitude of the earthquake does not vary from place to place. The magnitude of the earthquake, which is measured by our Indian observatories, it will be same if it is measured by American observatories or whatever. So magnitude of the scale does not vary from scale to scale, from place to place. Whereas intensity of that earthquake or the degree of damage of the earthquake varies from place to place. The earthquake has totally collapsed this building, but that earthquake made hardly crack or no damage to a building some 200 kilometers away. So it varies from place to place. So that is the intensity. So maximum intensity is 8 or 10 or 11 or 12. That is in Romanian script we express, and that is the we call it mesoseismal area or maximum intensity. What is the maximum damage has occurred, that is the maximum intensity. And some area is felt, so that intensity is of the order of 4 or 5, just felt. Or some crack, maybe intensity 6 or something. Some major damages, maybe it's a subjective, it's a descriptive scale. It's not mathematical scale. So that is the difference between, but that it requires expertise, and GSI I think is the best or most experienced organization, and their intensity measurement should be taken as much precise. So intensity has got also the first intensity scale, this Rossiforel, then modified. This is the till today it is used modified Mercalli scale. But again, like moment magnitude, this intensity MSK intensity is much further defined, further improved. So there are different magnitude scale. Magnitude does not vary from place to place, but there are also various intensity scale. Intensity means which varies from place to place. So these are the two basic difference. Next, basic difference of intensity and magnitude. Please remember that. And next one. So you have located earthquakes, you have estimated magnitude, you have also estimated by field survey. Intensity cannot be, cannot be estimated from the seismological records. From the seismogram, you don't measure the intensity. You go to field, go to site, go to see the damages. Somewhere it is liquefaction, somewhere total damage. So you observe those points and then make a contour of the same damages, and you call it isoseismal map or intensity map. So intensity is based on field observation, based on survey, and location, magnitude are all based on instrumental records. Now, having done that, you have located the earthquakes. For research also you have imaged the structure, where is the low velocity structure, where is fault, and what depth. All these things can be imaged. That you have done by inversion technique, seismic tomography. So having done all this, now we have to understand what was the process of that earthquake, how that earthquake occurred, by what faulting. Now I think geologists or geophysicists, they will be more interested in this. And also I think for anybody, for civil engineers also, they have to understand, because a thrust earthquake has got a different impact than a normal earthquake, normal fault earthquake or strike fault earthquake. As in my keynote address, I told that only thrust fault earthquake can cause tsunami. A strike slip faulting earthquake cannot cause tsunami, or even normal faulting earthquakes. After we didn't have, just by the way, we didn't have tsunami system in India. After the Sumatra earthquake, we made a tsunami system in India. And they, sometime in 2012 or 2008, they made a warning for the tsunami immediately from the earthquake record. Then they found the mechanism was strike slip. Then within half an hour, they announced that it will not cause tsunami. So tsunami caused by very great, large earthquakes and by thrust faulting mechanism. It has occurred in the sea area. Anyway, so different mechanism has got different impact. A thrust faulting earthquakes can do more damage than a strike slip or normal faulting earthquakes. So now to understand that mechanism of the earthquakes, this mechanism again we have first learned this mechanism or started to learning this mechanism since 1960s. So everything very young. It is based on the Reid's elastic rebound theory. You might have heard this name, Reid's elastic rebound theory. Based on that theory, the focal mechanism concept came. It is a geological concept, but is applied to understand the earthquake tectonics from that technique. So suppose your rock formation strata is like this, there is a fault and there is a tectonic stress due to plate movement or whatever causes. So that movement, the formation is taking up, and there is this type of shear type of movement this side and that side, the stress. So that stress is being taken up, but when the elastic limit reaches, then that fault or that formation breaks and rebounds, like you go on winding up the spring and it breaks and rebounds. Similarly, rock formation, it takes up the stress and then it breaks and rebounds. Rebound means like this, it moves. Like this it moves. You have seen here, it is taken up the stress and now it has broken and this formation has gone up there. So there is a break here, there is a movement, some strike slip movement or whatever, some 5 meters or 10 meters movement of the formation. So if that is the happening, then what will be the nature of the seismic wave motion? Suppose this is your fault line, you imagine one auxiliary plane. I am just giving you some idea how they do it, but to do it you need more illustration, but just I am giving you a little bit idea how they do it. So suppose you have stations in this, and this is a fault and this is an imaginary plane. So if your ground movement is like this, which is like this here, then in this part, if there is an instrument, your instrument seismometer, it will first pick up the POA motion up. But in this part, if there is a instrument, it will pick up a lower down motion of the POA. You understand my point? So depending on the ground motion, your first P arrival will be either up, we call it positive, or down. Similarly, in this quadrant, the ground movement is like this, so it will be we call it dilatation and compression. So these are the instrumental data, POA first motion, how it is recorded in different sites. Some station in Mizoram, some in Jorhat, some in Shillong. So all those data, POA first motions are plotted by some geologic technique, we call it stereographic technique. Geography also use their map by stereographic projection, because the globe is there, so they have to make a map so that area should not be distorted. So that area is maintained. So that is called stereographic equal area projection. So geologists and geographists also use this technique. So that technique is used, and it is plotted on a stereograph net. I cannot go into details. This is really, it takes some few hours to make you understand, but just learn from this lecture that the earthquake process, whether it is by thrust faulting or normal faulting or strike slip faulting, can be done from the POA first motion. Now with the invent of the digital instruments, we can do it by waveform inversion. One of our research student here, he is sitting here, he has already done some exercise and brought out a fault plane solution of the local earthquake here from one station. This is not very stable but fairly good. one station solution. Normally we take at least some few stations. For fast motion, we take no less than 20 stations. But for waveform inversion from the digital seismograph, 3-4 stations is better, minimum. More is the better, best. But one station data can also give us some fault plane solution, and I think I was so glad to see that solution. My mic is gone, I think. You want this? Can I move? No, I cannot move. I think I have hardly 5-10 minutes, so I'll just can you put it? All connected, no? Can you give me a bottle of water, please? Thank you. Now, this is how we do it. Now, how we interpret those solutions? We bring out such a plot and make the these black dots up motion as dark, and this directional quadrant as a white part like this here, and this is the solution of this earthquake by waveform inversion. Now, how we interpret? Next one, please. Now, these are the different beach balls you might have seen in some publications or in book or in research papers. That this type of beach balls or fault plane solution they show and they talk about this. So again, it is a lengthy thing, but just have a glimpse how this is thrust faulting beach ball. Means we are representing thrust fault by this type of symbol, and this is the the stress. We call it, geologists call it sigma 1, sigma 2, sigma 3. We call it P axis, T axis and B axis, means compressional stress, tensional stress and intermediate stress. So when the compressional stress is horizontal, say in the Himalaya, the head-on collision of the two plates, so there is a compressional stress is much dominant. So in that type of region, you will get mostly the thrust faulting. But when the tensional stress is more dominant, say in the case of a spreading zone, there is from both sides there is a moment, so there is a tensional stress. So at a tensional stress when dominant and horizontal, you will get normal faulting. And when both compressional stress, tensional stress are horizontal, there's a shear stress, you can say, you will get strike slip faulting. So that is what is shown here, stress system and the fault plane solution symbols. But it is not like this textbook type of solutions you get. So you get all sorts of mixture. So some are dominantly say thrust faulting, but with some strike slip component. It means that there is a thrust faulting, means one block has gone above the other, thrust faulting, but some strike slip movement also, means it cannot go just like this. It might have gone like this. So thrust faulting with some strike slip component. So that is the symbol. Normal faulting with some strike slip component. So like that, you have got different mixture, and we try to interpret. And then, what is the fault plane? I may have to go back to, but if you remember, I have said that one fault and one is auxiliary plane. So out of these two nodal plane, one is fault plane, one is auxiliary plane. Now, which is the fault plane? How to interpret which is the fault plane? So suppose this is the anything. Suppose this is the solution you get, a strike slip solution. Now there are two, we call it nodal plane, which has, or two planes which has separated this quadrant of direction and compression. Now which plane is fault plane? So that you have to take the help of geology. In that area, what is the strike of the fault and whether it matches with the fault plane solutions. If suppose this east-west fault is there, then you are most likely this nodal plane is the fault plane. So like that we try to interpret. There are other ways also to interpret fault plane. So this is the broadly how the seismologists locate the earthquakes, scan the structure, and then try to understand the generating process of the earthquakes. What type of faulting it has caused the earthquakes. Next one, please. Oh, I think I've done. I'm on dot. Thank you so much. So if there is any question, please, we can have 5-6 minutes or whatever. Yes, any doubt, if you have, I can clarify.
Okay, sir. Thanks for
Okay.
the presentation. It's a really brilliant presentation. My first question is that hypocentral distance, or we can say focal distance. The equation is B is equal to 8
Oh.
ds minus 2p.
I didn't give the details. You can see in my book. Can you go back to that slide? Yeah. That is not. That is just algebraically you can find out. That is the details is given in my book. Now this is possibly if I understand your question, how this is coming. This is coming. You can find out the. You can find out the travel time of the P wave. Suppose this is the distance d, then what is the travel time for the P wave? Velocity of P wave. So d by velocity of P wave. So d by Vp. You can see in my. I can give you my books soft copy to you, but I explain you your question. So this distance is traveled by the P wave from this hypocenter to this station. Okay. So what is the time period for T for the P wave to come? Suppose we call it origin time. When the earthquake is originated, from that time, how much time it has taken to come to that station? So that depends on the distance and velocity of the P wave. So d by P is the of the time taken by the P. And what is the time taken by the S? D by Vs, velocity of the S wave. You take the difference. You will come out with this considering Vp by Vs is equal to 1.73. This will come. The details is given in my book. So based on this, algebraically, based on this is physics. Based on this, travel time taken by the P wave and travel time taken by the S wave, if you take the difference, then S minus P time will give you about 8, considering the Vp by Vs or Poisson ratio of the earth is 0.2 or Vp by Vs is 1.73 or something like that. Based on that assumption, you will come out this distance is S minus P times 8 times. Yes.
Yes, I understand. But mostly like Ts minus dp divided by root 3 minus 1. Root 3 will be 1.732.
Yeah.
So root 3 minus 1 will be.
Yeah.
If we divide 1 by 0.3, it will be around 1.3. I'm a little bit.
Okay, I will show you in my book. I will show you. This is not. This is based on assumption. This will come like this. About 8 times of the S minus P time, and based on that, they used to draw the curve. Yes.
Thank you. And what about the Richter scale? When we talk about Richter scale, what is the magnitude? Local or
Local.
So
If you allow me another 1 minute, I can explain you. Please, can you go back to the Richter scale? I didn't go to that, deep into that. Last time I was given much more time to come to the scale magnitude. Yeah, please. Now Richter scale is defined. Just graphical method I made you understand that how just from the ESMA-SP time and amplitude, you can find out the Richter magnitude. Now, what is the base of this Richter magnitude? Richter assumed that an earthquake which has occurred at a distance of 100 kilometers and recorded by the instrument at that observatory by 1 millimeter, then that earthquake, he assumed its magnitude is 3. This is a basic assumption. So a earthquake at a distance of 100 kilometers recorded with 1 millimeter amplitude is considered to be magnitude 3. That is why in Richter scale there is minus magnitude also. So based on that magnitude, he developed this scale. Yes, what is your query?
Yes, sir.
So you say local magnitude.
Okay, sir. You talk about MS. The MS will be separated at around 8, right? 8 magnitude. Surface magnitude, sorry.
Yeah.
The saturation value will be around 8. So you talk about that it's overestimate. When according to my knowledge, actually moment magnitude also overestimate till 6 magnitude. That's why we still use Richter magnitude if the earthquake is lower than 6. If it exceeds 6 magnitude, we use moment magnitude.
Yeah.
Is it right?
Yeah.
So
Normally Richter magnitude saturates over 6. So up to 6 magnitude, Richter estimated magnitude and moment magnitude estimated magnitude is compatible. They are almost same. But beyond 6 magnitude, in Richter scale, say 7 magnitude, that is normally I suppose it will be little underestimated because it saturates when it is more than 7 or more than 6.5. So maybe moment magnitude is more stable. Yeah.
okay, sir. So my point is Richter magnitude still dependable? Can we still depend if the magnitude is lower than 6, or will use moment magnitude for the whole earthquake?
That's a good question. Well, nowadays with digital instruments, since we have no analog instruments now, we are mostly not going for Richter magnitude. We are now, built-in software is there. I think he is there. He is doing this job. So it is a built-in software is there, and we are for any digital records we are straight away estimating MW. In those days there was no digital instrument, so Richter magnitude was the only scale to be estimated. And nowadays the old catalog, those magnitudes which are given in the Richter scale, now those magnitudes are being converted to MW because for other studies they are making it a homogeneous magnitude. So that is a different aspect. So in the earlier catalog of the earthquake catalog, you will find that magnitude is given in MS or MB or Richter, various scales they have used. But since I think maybe 2010 or so, I think any catalog and every catalog is now maintaining MW. Yeah.
Two questions.
Yeah.
First is that what Professor Sati during his introductory remarks, he mentioned that there's a school of thought which says that number of frequent small earthquakes will help to avoid a larger earthquake.
No, I don't think. I got your question.
Okay. What is that, sir? And second is that since childhood we have heard that animals have this capability to
Sense.
foresense that
That I have told also.
earthquakes.
Yeah.
And even videos were circulated after this Turkey earthquake that they could hear something, because yes, there are auditory buds where they can hear and we can't hear. But has some study been done in this areas, in this field?
Okay. Two good questions. First question I will take up later elaborately. I will show how it is done. He talked about, I think your question was more popular question, whether, because small earthquakes, there is a B value, we all heard about it. The B value is a relation between earthquake, number of earthquakes and magnitude of earthquakes. Means with the magnitude, one magnitude down, the number of earthquakes goes 10 times. Suppose in Mizoram, one earthquake occurs magnitude 6 in a year. Then you can expect 10 earthquakes of magnitude 5 in a year. 100 magnitude 4 in a year. 1000 magnitude 3 in a year. So that is the power law again. I talked about energy in a power law 30 times, 34 times. Similarly, number of earthquakes increases by 10 times with 1 unit of magnitude down. So that is called, and that relation slope is called B value. I will take up that in technical session. Now your question was very pertinent to understand this point. And some speaker says that when there are smaller earthquakes, the stress is released and fear of large earthquakes is reduced. No, at least as a seismologist and from my experience, the answer is no. I will tell you that smaller earthquakes energy does not release the stress which is getting accumulated over hundreds of years. Say an example I am giving you, in Bhuj, the magnitude 7.7 earthquakes, the energy release was some 10 to the some I forget the exact figure, some energy was released, and then immediately within 24 hours we went there and recorded some 6,000 aftershocks from magnitude 1.5 to 4 up to 5 and 6, I think hardly 1 or 6. So magnitude 4, 5, 3, some 6,000 earthquakes we recorded, and total 6,000 earthquakes energy release was not even 1/100th of the main shock release, energy release. So it is said, smaller earthquakes happening, so large earthquakes will not happen, stress is released. The concept is wrong. The Chinese says, smaller earthquakes every day, bigger one on the way. And you had another question.
That is regarding pre-sensing of these activities.
Yes, I think in my keynote address I have mentioned that point. It is not circumstant, it is not always observed. Suppose your dog is barking at night, you will say, evacuate the house, dog is barking and abnormally barking and there will be earthquake. I have also observed, one earthquake occurred when I was in the field in New Zealand. One, horse was snoring in the night, and there was earthquake. Possibly there was, but that earthquake was not felt. But so we cannot correlate, except the Haicheng earthquake, where there was really abnormal behavior of the underground snakes. They had some, before the earthquake, there is some electromagnetic emission. So because of the, there is some dilatation hypothesis of some fracture happening. Minor cracks is happening, some flow of fluids, flow of water or whatever, some flowing, so there is electron movement. So some electromagnetic signal is sensed by the underground animals, insects. But it is not observed all the time. Say, I told you 1975 Haicheng earthquake, there was abnormal behavior of the underground insects, but in 1976 earthquake, there was no abnormal behavior. So from animal behavior, only in the history of mankind, only one earthquake on animal behavior was not predicted, was announced, you evacuate your house. And it really worked. But yes, your question was whether we have done some work in this field. One possibly have heard the name of Professor Bapat, who used to predict earthquakes every now and then in newspaper for Northeast India, some 30, 40 years ago. Now he is no more forecasting earthquakes. I don't believe this prediction of earthquakes. Anyway. So he was in the very last stage, means I met him maybe 10 years ago. He was working on this aspect, animal behavior. but I didn't see any publications or any report. There's no published report on animal behavior research in India. But one person, he was doing some work that I heard, but no publication I have noticed. But as I said, some cat is barking, doing mewing, or dog is barking, you cannot say earthquake is coming. It is difficult. It is not. Animal behavior is always not observed. Any other questions? Or if no questions, then yes. Yeah.
Okay, thank you, sir. If there is no more questions from the audience or participants, let me conclude this is covering a wide range of topics, like from the historical development of earthquake observatory in India, and brief history about the transformation of analog to digital system of seismogram, and how to locate the epicenter of the earthquake, and different scales for measurement of the earthquake intensity or magnitude, and even topics like the source mechanism, like for the candidates like from the disaster management students, those who are not having geology background may really needs to understand about the geology, how the mechanism of earth dynamics can cause and leads to the earthquake incidents. So dynamics of faulting, thrusting. So I think many of the geology students may also understood based on his talk about how different types of fault can cause different kind of earthquake seismicity, like types of earthquake intensity, and even the tsunami. Just now from his talk, sir, I understood that thrust fault can lead to this kind of tsunamis, but not by the this transform fault. So it is very informative, sir. Your talk is very nice and good, and very informative for the students as well as for the faculty gathering here. So with these few words, I will conclude the talk. Then if the organizing secretary may be invited for some other announcement, please.
Thank you, a respected invited speaker. May I request Professor Rao of Geology? Sorry, there are two Rao here. So to present memento to our invited speaker. Sure, please come.
It is a very great opportunity to honor international.
Thank you, sir. So now let me invite our co-convener to present a certificate to our chair. Dr. Zonana, please. Okay, thank you all. So now we will have a lunch break. So up to 1:30, according to the program, but you may extend to up to 1:45. So the second technical session will start at 1:45, please. So all are invited to attend. Thank you all.
Okay. So, may I have your attention? Okay, so now we start technical session 2. This
ฮัลโหลซงครับฮัลโหลซงพัน
서팀서 촬영을 해요. Để nó ngay cái office ở cái hành cần là gì vậy? Okay, sir. Okay, okay.
Let us go to part 2. Yes.
This is for video.
Okay. So, good afternoon to all of you and to the chairpersons here. It's again nice to be with you and discuss something on the part 2 of our lecture, that is on earthquake source zones. I am not going to cover the peninsular India or Himalaya. We will just focus on this part because our title says in NER. Now, what are the different earthquake source zones? One student came to me to know how to select areas, whether by rectangle or circle or elliptical, to find the B values. And some students try to know, what are the different short period, long period, broadband, what does all this mean? So many doubts will be there. And in a one day, as much as we can try to understand, we will try to understand. Next slide, please. So this is, I will now try to understand the source zones of Northeast India. Broadly, you can see here, as I said, from Carlsberg Ridge, the Indian plate is moving. I don't know, it's not working or what. So it is Indian plate is something like 60-70 million years ago. The Indian plate was in this position, and now it is on head-on collision with the Eurasian plate, and the present position of the Indian plate is like this. And in the next picture, coming now. Can you see? Oh yes. So this is how the Indian plate over the last 60 million years it has moved. I think it is the fastest plate on the earth, which has moved a long distance from Antarctica and now on head-on collision with India, with Eurasian plate, and Himalaya has come up because of that collision. So there was a Tethys Sea, all sea, and the Pangaea, the main say piece of land, that broke, and that then started moving. So Indian plate was with Antarctica, and then it broke, and then it started moving. So this is the present situation, and you can see Indian plate is very interesting that way. This is the Carlsberg Ridge. The Carlsberg Ridge so I think it's 80 degrees. Carlsberg is further this side. It is not shown in this map. So that's a spreading ridge. This is. There are two types of ridge. One is on the ocean floor you find this type of ridge. This is called 80 degrees. This is called 90 degree east ridge, and there are so many seamounts, this, that. So ocean floor is full of lot of topographical changes, and the spreading ridge is where from the zigzag fractured zones and the material comes and spreads. So Indian plate is from the spreading ridge. The Carlsberg Ridge is named, and Indian plate is moving. And this is the Carlsberg Ridge. The earthquakes are also along the spreading ridge. Here the earthquakes are not very high magnitude, maybe within 5 or 5.5, 6, very rarely. So this is the spreading ridge, Carlsberg Ridge, and from that is also marked by this seismicity. And the Indian plate is moving, the whole Indian lithosphere is moving, and this is the continental part of the Indian plate. Now it is hitting with the Eurasian continents. So it is a continent-continent collision, head-on collision. And then the oceanic part of the plate, as I said in the last lecture, that the plate is moving, and when it gets some trench, खाद जिसको बोलते हैं, वो that is consumed, that goes down to the खाद, down to the trench. So there is a subduction tectonics along this, this is Andaman, Nicobar Island, this is Sumatra, this is further there, this side is Java. So along this trench, the oceanic plate is subducting, and the continental part of the Indian plate is on here. So there is a collision zone here, and there is a subduction zone, and this subduction zone, it seems, is connected with the Indo-Burma ranges. There was sea, and then it closed, and now there is Burmese plate and Indian plate. Now they are on, interaction, but that subduction structure seems to be still existing. So that is how this subduction process up to this, this Indo-Burma ranges means this is the syntaxic zone. So this is the subduction zone which is continuing down to this trench also. So there is a we can call it atypical subduction. Normally subduction is oceanic floor subducts in a trench. But here the continental part of the Indian plate, say northeast Indian part of the Indian plate, easternmost part, is still subducting, it seems. Some people do not believe subduction, they believe that it was subducted plate is now being dragged. So because of the plate movement. Anyway, so that is a different topic. So, so you can see that whole Himalayan area is zone is collision tectonics and earthquakes. Indo-Burma is, I think, intense active, and there is little gap here, the Irrawaddy basin, that maybe the stress is creeping due to the sediments over here, and then the Andaman and Sumatra trench is very active and lot of earthquakes. Now, when you examine the structure, there are a lot of east-west structures. The sections are taken along this. So this is that AB, I suppose, the northern. So you can see that Indian plate below the Indo-Burma range is still going down to 200 kilometers or so. Here also in the Sumatra, this is going down to 300, 400 kilometers. Further south, going down to something like that, 400 to 500. But in the Java, this part, the plate is down to, I think this is the deepest subduction zone, up to 660 kilometers. So, and this subduction structure is very much well reflected in the earthquake sections, say hypocentres or whatever. We take this section means, all geologists will know how to do the sections. They plot it on that section, and then at depth they plot it. So when you plot it at the depth, we call it also depth section, it looks like the below Andaman, below Indo-Burma ranges and this Andaman Sumatra, this is a seismic, we call it seismic zone or Benioff zone. So this is the structure. So very clearly it is visible that the subduction is still going on. And this is what is happening in the Himalayan region. The Indian plate is not subducting, but gently dipping below the, Tibetan plate, and Himalaya has come up by due to the interaction, the collision. So here the earthquakes are shallow, down to 20 kilometers. Indian plate is just gently dipping, not subducting below 100, 200 kilometer depth. Whereas here it is. And this is what is Indian plate at the subduction zone, trenches. This is Indian plate subducting below in Andaman Sumatra subduction zone. So this subduction and collision, I think it is a bit clear to you. Continent-continent collision, and oceanic plate subduct below the trenches. Next one, please. Now this is our old work, I think 1996, and we tried to understand the structure, which is the first slide was a recent study and this was our old study. So we actually demarcated that the structure along this Arunachal cross section, it is earthquakes are more or less confined within 60-70 kilometer. There is no subduction structure. But as you come to this Shillong Plateau and this Indo-Burma ranges, the structure is very visible, and along this Bengal Basin and Indo-Burma ranges, the structure is very visible. And I try to draw this boundary from the plate interface, from the thrust faulting zone. This is the thrust faulting zone, and this is the inside the. I'll show you all those solutions. From the thrust and normal faulting region, this plate interface is drawn, and this is the envelope. So this is about 30-40 kilometer width of the seismic zone. We call it Benioff zone, that is below Indo-Burma ranges, and also further south below over here. And this is the section along the strike of the Indo-Burma ranges, and you can see it's down to 200 kilometers. The earthquakes are all along the Indo-Burma ranges along the strike, but as you go beyond 26 degree, the earthquakes are shallow. So below 27 much shallow. So that means subduction ceases beyond 26 degree latitude. There is no more subduction or no more deeper earthquakes beyond 26 degrees. So this is, we call it a syntaxis zone. So subduction from 26 degree latitude down to Andaman Nicobar Island, that structure is there, but not below this syntaxis zone. And this is what we try to do, the gravity anomaly, how this structure is matching with the gravity gravity anomaly. This is the geophysical observation from gravity map. This is the gravity map of the whole northeast India. You can see the Dauki fault is in the very close contour. You can see here a fault is demarcated here, the Dauki fault, long fault, and here you can see the Himalaya, the all MCT, MBT are all the steep gradient of the anomaly map so indicates that fault, and you can see the Shillong Plateau is having higher gravity anomaly. So this is another geophysical observations to understand the tectonics and how gravity structure is also matching with this seismological structure that we brought out from the seismic data. So seismic data and gravity data are studied to understand the subduction structure below Indo-Burma ranges. Next one. This is again with better data, better location. One, I think, if any one of you work with, this type of work means to understand the structure, to do the depth section of the earthquakes, you always go for the EHB data. In the ISC catalog, there will be a different catalog named EHB catalog in the same bulletin. EHB catalog is some Ingdal, Harvest and some Bullard. They relocated the earthquakes, ISC earthquakes, and with a better depth. So depth is better in this catalog. Anyway, so these data are again studied, and same picture you can see with the recent data. You can see that here it is of that range. No subduction in the Arunachal, Himalaya or in the syntaxis zone, but subduction structure below Shillong and not below Shillong, below Indo-Burma ranges along this structure, along Shillong, and this is the 1897 great earthquake here. So it is away from the subduction structure. We normally call it intraplate earthquakes. Intraplate earthquake means where the plate is subducting from their boundary about 100 kilometers away from the boundary zone. We call them intraplate earthquakes. And the earthquakes which are occurring in the subduction zone called interplate earthquakes. And the earthquakes also in the Himalaya, they are also interplate earthquakes. But the earthquakes in Kilari or in Jabalpur, they are intraplate earthquakes. So interplate earthquake means in the collision zone or in the subduction zone. And away from that interplate or for the plate boundary, the earthquakes are called intraplate. So we can call this Shillong Plateau earthquake intraplate earthquake, and a great earthquake. This is not a subduction structure earthquake. But there are a lot of earthquakes in the subduction structure also. And this is the same along the strike. So with the much precise data also, the earlier work was based on USGS data, but now with much precise data also, it is giving the same. Next one, please. This is also a recent publication by NGRI, Rao and Kalpana. They have studied they tried to demarcate the thrust zone and normal faulting strike slip zone. So this part of the within the subducted plate, say, this is the envelope of this Benioff zone. Up to 90 kilometer depth, the earthquakes are mostly, normal faulting earthquakes, red marks. These reds are normal and strike slip. If you can remember the beach balls, they are normally normal. This is normal. If you can see my light, normal. This is strike slip. So normal and strike slip faulting red, and the blue is mostly thrust faulting, or with some strike slip component. So these blue or these thrust faulting earthquakes are below 90 kilometer depth. In general, generalized. So they say that it is why it is nicely it can be explained. In the upper part of the plate, when the plate is bending, because of the bending stress, there will be, tensional stress will be more dominant. And as I said in the last class, in last session, that when the tensional stress is dominant, the normal faulting occurs. And when the compressional stress dominates, the thrust faulting occurs. So that is the stress system, and when both the stresses are horizontal or shear stress is dominant, then strike slip faulting occurs. So they demarcated thrust faulting zone and normal, this is the normal faulting zone and thrust faulting zone. And this thrust faulting is explained that when it is going down, the asthenosphere is giving the resistance. So a thrust, or a resistance, or two forces, compressional stresses are there, and which is causing this thrust faulting zone. So this is how they made a demarcation that less than 90 kilometer depth earthquakes are normally this, and more than 90 kilometer depth are most normally thrust faulting. Next one. This is an interesting study that we made with Russian collaboration, Kayal group, and just to give you some idea about what is happening. This is seismic tomography, and this is not a very very local tomography, very detailed tomography of only for this, say, Mizoram area or some Shillong Plateau area. This is for the whole region, for the whole Northeast India. In his first study, Kayal showed like this, that this is the section which is possibly crossing Shillong Plateau and Indo-Burma ranges. In this section, he has shown that the subducting structure, this is that structure, is going further down up to maybe something like 400 kilometers or so, and upper part is here, and there is some break over here. Then we made, this is his earlier publication, then we made a very detailed study taking our local, whole Northeast India data, and we tried to make a detailed study up to 100 kilometers, and then we found that this is, our study is also matching with his regional study. Means there is a subducting high velocity structure which is continuing, of course this is his study, which is continuing down to 400 kilometers. So, but earthquakes are confined only down to 200 kilometers. So there is a model which matches very well. This is normally the normal faulting zone, this is normal faulting, this is thrust faulting, this is normal faulting, this is thrust faulting. Just now we have seen in the Burma ranges, Rao and Kalpana's. Now this is a structure which is possibly can explain this type of broken. Sometimes though due to temperature effect or whatever, the lower part is broken and it is no more seismically active, and the upper part is seismically active. Possibly that is the case with the subduction structure below Indo-Burma ranges today. So upper 200 kilometers is seismically active and lower part is dormant. Next one. But it was there, in geological time. Now we are coming to earthquake source zones in Northeast India. I gave some background of the whole region. Now let us see what is happening here. So now you understand what is interplate earthquakes and what is intraplate earthquakes. So in the Himalayan collision zone, we have Assam Great Earthquake, and I have written 8.4. But one should be careful what he is writing. I am writing MW. So, and this is revised MW. This is published material, means MS is now revised to MW 8.4, MS 8.7 revised to 8.4. And that is the largest earthquake in the Himalaya so far we have recorded, 8.4. MW 8.4. And then we had recently 2009 MW 6.3 earthquake. Bhutan earthquake you might have felt also. And then Sikkim earthquake 6.9, almost 7 large earthquakes. That is 2011. So these three are recent earthquakes in the collision zone over here, you can say, and these are the magnitudes. Now in the IBR subduction zone, there is something like 25 or something like 20 large earthquakes in the IBR. And most recently, I think I have recorded some 1988. It was at 100 kilometers. This earthquake, you remember, this was a forecast by Gupta and Singh. I will come to that. Then 2015, there was another earthquake, 6.5, 10 kilometer depth, and then 2016, the Manipur Impal earthquake over here, somewhere. I think this is 2016, somewhere here, or maybe this one. Yes, 2016. So there is a 2016 earthquake, Manipur earthquake. Then Mizoram earthquake, I will come more details to that. There are some earthquake swarm, and it could be a precursor. I will come to that in earthquake prediction topic. So there is no large or very strong earthquakes. Normally 6 and above we call strong, 7 and above we call large, 8 and above we call great, and 9 and above we call mega earthquake. So Mizoram had a abnormal seismic activity in 2020. Some 7 earthquakes magnitude 5 to 5.9. I think 3-4 of them were oil felt in this part of the country. And I think I came last year. We had discussion on this. Then the intraplate earthquakes. Now you have known the interplate earthquakes, Himalaya and in the Burma ranges. Now there are intraplate earthquakes. Northeast India is very unique. It has also got intraplate earthquake source zones. Intraplate means which are not directly due to not directly, but due to collision, but not directly due to collision. The stress from the collision zone or from the subduction zone is transmitted to the intraplate region, and earthquakes are caused. So they are intraplate earthquakes. And there are Assam earthquake Kopili fault. This 1869, remember this. This is the Kopili fault I have shown from microseismicity map. One student was asking microseismicity. So I will come to that later on. So this is large earthquakes I am showing. You see, this is the long Kopili fault, about 300 kilometers or more than that. And at the end of the Kopili fault here, which is meeting here at this junction, Naga thrust and the what do you call it, Daugi fault, and Kopili at this junction 1869 revised again 7.4 MW. I am talking only about MW. And this is 1943 7.2. 2 large earthquakes already occurred on the Kopili fault. And most recently 6.1 Sonitpur. And also this one I suppose, 2016 earthquake, Manipur earthquake could be Kopili fault earthquake. I will come to that. So Kopili fault is the most vulnerable earthquake source zone in NER, and intraplate earthquake source zone. And its intraplate earthquakes are dangerous. In a sense, they are mostly shallow. Luckily, Kopili fault earthquakes can go down to 30, 40 kilometer depth. But intraplate earthquakes is always, you can see that Kilari earthquake, intraplate earthquakes, 6.3 magnitude, killed some 20,000 people and total damage. So intraplate earthquakes are normally shallow, 10 kilometer, typical intraplate earthquakes. Kopili fault somehow down to 30, 35 kilometer depth is active. And Shillong Plateau, also another intraplate zone, and it is its tectonics is, this is strike-slip tectonics, Kopili fault. And this is another zone, intraplate earthquakes, where this 1897 earthquake occurs, and it is pop-up tectonics. So two different tectonics, rather four different types of tectonics are going on in NER. Collision zone in the Himalaya, another is syntaxis zone in the this part where Himalayan belt, I think this battery is down. Himalayan arc and the Burmese arc is meeting, that is called syntaxis zone, joining place, which produce the largest earthquake in the Himalaya. And I think you have to give battery to this. And another source zone is Shillong Plateau, and this is pop-up tectonics. And the other source zone is Bengal Basin. So that is not adjoining area. So these are the large and great earthquakes and strong earthquakes, most recently some strong earthquakes. And Tripura also had a well-felt earthquakes. So at a glance, these are the reds are the past earthquakes, and the black stars are the very recent earthquakes. And by the way, I can say that the Assam earthquake, yes, now it is working. Assam earthquake, one more. Okay. Yes. Now, by the way, I say that this earthquake occur by strike slip. Now you understand this beach ball. This is strike slip earthquakes. So it is not a typical Himalayan shallow 20-kilometer thrust fault earthquakes. All earthquakes in the Himalaya are mostly thrust, but this is strike slip. And what else I would say? And Shillong Plateau earthquakes, it was a reverse fault. Thrust fault and reverse fault are same. It's thrust faulting only, because this symbol is, as I said, this is thrust faulting. But when it is called reverse, when the dipping plane is more than 45 degree, geologically, that is how it is defined, then that fault is called reverse fault. So the dipping plane of this fault plane is more than about 60 degrees. So this thrust faulting is also called reverse faulting. So Shillong Plateau earthquake is a reverse faulting earthquakes and by pop-up tectonics. Next slide. Yes, so first let us try to understand the Shillong Plateau pop-up tectonics earthquake source zone. Shillong Plateau is a very vulnerable, already produced great earthquake. It was magnitude MS 8.6, now it is revised to MW 8.1. So, and it is initially it was thought to be a Himalayan earthquakes. In the Himalayan earthquakes, in the past literature, you will find this is included in the Himalayan earthquakes. But now seismologists do not believe it to be Himalayan earthquakes. It is an intraplate earthquakes, not a Himalayan collision zone earthquakes. It is intraplate earthquakes, and a tectonics is different. Its tectonics is, this is that structure I have already explained. This is the 1897 Great Shillong earthquake, and the subduction starts from somewhere from here, where the plate flexes. And this is the model is given by Bilham in England based on their GPS data. Shillong Plateau is popping up, there is no doubt about that. That was also by past records from the geodetic data. It is something like of 1 to 2 millimeter rise in last 50 years or last 70 years or so. So Shillong Plateau is popping up, and the boundary fault is demarcated by this Dauki fault, which is separating Bengal Basin and the Archean niche, that Shillong Plateau. It's a part of the Indian Peninsula Shield actually. It's a shield part. It's a granite niche. So this Dauki fault, if you go to field, even a non-geologist can see the fault. Means it is so much demarcated. The Bengal Basin is down there, and you are standing on the Shillong Plateau high. So there is a down thrown there. And he said that from the geologic data, he said that there is a fault here, and between this fault, he named it Oldham Fault. He means Bilham in England. And this proposed that between this Oldham Fault and the Dauki Fault, Shillong Plateau is popping up. Popping up is recorded from GPS data. And they say it's popping up, pop-up tectonics, and that caused the, in the South Dipping Fault, means this fault, Brahmaputra Fault, this South Dipping Fault rather Oldham Fault they call it. I made a mistake. They call it Brahmaputra Fault from GSI. I will come to that. So they gave the model between Oldham Fault and Daugi Fault. Shillong Plateau is popping up, and this Oldham Fault is the causative fault for the Shillong Plateau earthquake. But for you, at a glance, you just remember that Shillong Plateau is a source zone of earthquake, intraplate source zone of earthquake in NER by pop-up tectonics. And this is the model. Now I will, and this is, I think I should mention that the intensity, you can see a hat type of structure of the order of 12 in mm scale, modified mm scale. And means total damage was there. And then intensity down to 6 or 5 is plotted. You can see this circle, if you can see. So intensity is, as you go far away, is felt, or some crack or something, some window cracking and swinging, all these things. So intensity 5. So it was felt about 500 or so kilometer away also. So intensity is 5. But the magnitude is 8.1 MW. So magnitude is fixed. Intensity varies from place to place. So now I think it's much clear to you what is intensity and what is magnitude. And Oldham observed that the boulders were thrown from their place and thrown out. He was a brilliant, brilliant geologist, first DG of GSI. And he, in his report, he gave that this earthquake must have caused a ground vibration of 1 G. 1 means ground acceleration of 1 G. And there was no strong motion instruments to record the acceleration. Nowadays we have got all instruments to record the acceleration, ground acceleration. What is the G value of that? That other day, in the morning we are listening that zone 5, zone 4, zone 3, all these things. Zone 5 means maximum ground acceleration can go up to 1 down, 0.4 G. Zone 4 means 0.3 G. So like that. So whole northeast India is vulnerable for ground acceleration of the order of 0.4 G. And he estimated for this earthquake, the ground acceleration was of 1 G, otherwise the boulder cannot be thrown into the sky and dropped. It must have exceeded the Earth's gravity field, and it must be 1 G. So today, modern seismologist, hats off to him, his estimate of ground acceleration. Okay, next slide. Now one student came to me about micro earthquakes, micro seismicity, and seismograph, all these things. Yes, this is what we are recording, micro seismicity by closed broadband network. In those days there are some 25 stations around this area, which was telemetrically recorded by the NIST Jorhat. So that project is over and that network is no more there. So those data we took and we tried to understand what is happening in Kopuli Fault and in Shillong Plateau. So these are the micro seismicity, micro earthquakes. Of course, they are 3 and above, not really micro. Micro means less than 3 is micro, and more than 3, they are called small earthquakes. Up to 5 is called medium magnitude, 6 strong. So these earthquakes were detailed, we studied, and you can see the fault plane solution of these earthquakes are studied. In Shillong Plateau, they are mostly, you can see, thrust faulting or reverse faulting, whatever you say. And Shillong Plateau mostly strike slip and normal faulting. So the mechanism, the source process of the earthquakes in Shillong Plateau is different, and in Kopuli Fault is different. And these two are the most vulnerable large earthquake source zones in northeast India. Next one. Then we studied the section of the earthquakes, means across the Shillong Plateau we took the section, and we found that earthquakes are like this. At depth we have, means along north-south section, and this is depth. And we find that this is a model, and in that zone, Shillong Plateau zone, down to up to I think 25-30 kilometer depth earthquakes are there, and these are the higher magnitude earthquakes, more than 4 or whatever. So And we also did the fault plane solutions, and those fault plane planes are, in fact, planes are also plotted. So what I want to say you that these earthquakes are definitely showing the Sri Lanka to tectonics, and fault planes are also showing that one is southern dipping fault, this is north-south, and one is rather this is northern dipping, this is southern. Two faults are there, and between these two boundary fault, the Sri Lanka plateau is popping up. But we could not resolve whether this is a Oldham fault or Brahmaputra fault. Geologists believe that that Brahmaputra river is a fault. The east-west trend of the Brahmaputra river to the north of Sri Lanka plateau is a fault. That is from GSI, geologists believe. And Bilham, some American seismologist, he, from his geodetic data, he, gave a fault which he named Oldham fault. But we cannot differentiate because they are so close, and any means pop-up tectonics is there, rise is there, and whether it is because the fault is not a line, it is zone. So it could be Brahmaputra fault is the boundary fault. So that's a bit argument is there. Next one. Now let us try to understand the Kopili fault. Again, from the small earthquakes, micro earthquakes, we are trying to understand the Kopili fault, nature of Kopili fault source zone. How is happening? You see, this is the whole Kopili fault zone. This boundary, this earthquakes means along about 100 km wide Kopili fault zone you have taken, where all the earthquakes are along the Kopili fault, and most of them are you can see strike slip, normal and strike slip, normal and strike slip. And the most recent earthquakes, that Sonitpur earthquake somewhere occur here by strike slip. Then we also inferred in one of our paper the Bhutan earthquake, 2009 earthquake, which is in Bhutan, in Himalaya. We also try to argue that the Kopili fault is hitting, the MCT. This is the MCT, main central thrust in the Himalaya, all parallel thrust zone in the Himalaya. And this is the MBT, main boundary thrust. So this Kopili fault hitting the MCT, and on that you can see a curvilinear structure is taken by the MCT, maybe due to Kopili fault transgressing into the Himalaya, and change the nature of the MCT, and earthquakes occur here. And the global solution has given a thrust faulting solution, because they all made in the fixed model of Himalayan earthquakes. And we took the 30 station around here and did the fault plane solution, and it was strike slip. This is our fault plane solution, the strike slip. So we inferred that could be the Kopili fault has a role in triggering the Bhutan earthquake. And the fault intersections are the most vulnerable zones for earthquakes. So that is Bhutan earthquake, could be Kopili fault is a reason. And the other one is Manipur earthquake, 2016. Now this is the Manipur earthquake, and this is the strike slip. And this fault plane, which is this nodal plane, is matching with the trend of the Kopili fault. And the aftershocks rupture also propagated to along the Kopili fault. I will show you more details afterwards. So what I want to tell you here, that Kopili fault is a long fault, and it has already produced two large earthquakes, 1869, 1943, and most recently Manipur, possibly Manipur earthquakes, and the Bhutan earthquake, and the Sonitpur Assam earthquake. So it is we can, seismologists can, in the morning I told you, seismologists can give you the earthquake source zones, which is vulnerable for earthquake, future earthquake, cannot predict earthquake with time, space and management. But we can say Kopili fault is a very vulnerable source zone for any other large earthquakes. Similarly, Sri Lanka plateau. In addition to Himalayan collision zone, and they are interplate earthquakes. Next one. One came to, I don't have detailed slide here, because for every topic I have given something like 30-40 minutes. So accordingly I have arranged my slides. I don't can't go on increasing the slides, hundreds of slides. I don't believe in that. So you can meet me again for detailed discussion. For B value, we have make a map here. You can plot that map. You can make that map, B value map. It's more informative. B value, I think, may not be. I might have just mentioned it. B value is a magnitude frequency relation. When you plot the magnitude and number of earthquakes, cumulative number of earthquakes, when you do research, you will learn more. But just for a general knowledge, you learn that it is a magnitude and the cumulative number of earthquakes. When they are plotted, a linear equation, a linear relation is found, and that slope is called B value. This much you know. There is a Gutenberg-Richter relation. They found this relation first. Based on this relation, actually, the micro-earthquake seismograph was developed. When they found that with magnitude 1 down, the earthquake goes 10 times in the power law, then the concept of micro-earthquake technology came. In 1980s or 70s, early 70s, micro-earthquake instruments was designed based on this Gutenberg-Richter relation in 1955. So, huge number of earthquakes you can record in a short time. You don't have to wait for for your observatory to record a earthquake of magnitude, because normal observatory in those days used to record only magnitude 4.5 and above. So when this relation was found, then high sensitivity micro-earthquake seismograph were developed to go to study the aftershocks or to study the active fault, whether this fault is active or not. For that, the micro-earthquake instruments were developed, and this works very so nicely. Now we are trying to understand. So these data in the whole Northeast India. So this is the relation, and there is a either just by least square feet or by maximum likelihood method you can find out the relation and get the B value. Now how this B value you will interpret. Normally normal B value, as I said, is 1 in the log scale. So 1 means with magnitude down with 1 it goes 10 times. In log scale it goes number of earthquakes. But B value is not always 1. It can be 0.5, 0.6, 0.9, 0.8 or more than 1. It depends on the tectonic region, and depends. In the Himalaya normally less than 1. In Northeast India also normally less than 1. Less than 1 normally it is interpreted that the area is under stress. Stress is not fully released. There is still stress to generate earthquakes. And more than 2 means more than 1 means it's a more smaller earthquakes are recorded and it is tectonically very active, like that. So stress are getting released or whatever way you interpret. But now one caution should be taken. First thing is that so I think someone is doing some project for his master degree. B value, you have to know the threshold value, cutoff value, above which your catalog is complete. Because in the catalog, they might have given the earthquakes magnitude 3 and above, but 3 is not the threshold value. Your catalog is not complete with magnitude 3. Some earthquakes were located magnitude 3 or 3.5, but all of them could not be located because the instruments may be far away, data may not be there. So from the this relation also you can find after certain magnitude, say magnitude 2 or 3, you can see a saturation. Means the linear line is not maintained. Linear relation is not maintained. That means beyond that magnitude, means magnitude 3 or magnitude whatever, the earthquake data is not complete. So that is called threshold magnitude. So before doing this B value research project, you take care of your threshold value, then take care of the magnitude in the old catalog and magnitude in the new catalog. They are not homogenized. You have to do homogenization. So B value is a small results, but a very hassle work. But this work I think can give you some fruitful results in a sense. One of my PhD students did this work. Huge data is there for last 50 years data we have studied. So every 10 kilometer, maybe I forget, maybe 20 kilometer, every 20 kilometer grid she made and then overlap. And this like this whole northeast India may be divided by some, something like 50 grids by overlapping, and for every grid, she made estimate the B value. You get my point? And in every grid, in every area, means 20 kilometer by 20 kilometer area, you have to have at least 50 data. To any statistical relation, you have to have at least 50 data to estimate B value. So like that, in every grid she made, and then plotted those values, and then made a contour. You see what a beautiful structure has come. This is huge data, some few thousands data, and by grid, she made, making grid 20 kilometer by 20 kilometer area, she estimated B value and plotted those B value and then made a contour. And you can see that Shillong Plateau has come up with some 0.8 or 0.9 structure, like a pop-up structure or circular structure, and Kopili Fault a very long transverse structure. So wonderful B value, I think, has given us a visual, you can see, structure from B value. And similarly, fractal dimension. This is another thing you can do. And same data, same grid. And fractal is, I think you understand or maybe heard about it. Fractal is, you know about 1D dimension, 2D, 3D, you know. And what is the dimension of fault? What is the dimension of a tree? What is the dimension of a sea coast? It's neither 2D nor 3D. So there is a fraction. So a fault structure is not a purely 2D or 3D or 1D. So there can be a fraction, so that is called fractal dimension. So the normally fault dimension is 1.5, 1.6, 1.7 we have found. So those fractal, and it is also similarly a relation is there is in my book, number of earthquakes and its frequency. So that way also she brought out a fractal dimension map, and this also show a structure here, Shillong Plateau pop-up structure and the Kopili Fault structure. And I mentioned about seismic tomography. You can see at any depth you can take a slice and see what is the structure there. At 10 kilometers, what is the structure? At 20 kilometers, what is the velocity structure? At your desired depths. And you can see that at shallow depth it is so heterogeneous. The blue is high velocity and red is low velocity, and you can see it's very heterogeneous structure below 10 kilometers, below Shillong Plateau and Kopili Fault. 20 kilometers also, these are the white dots are the earthquakes. So there is a high velocity structure, something like Shillong Plateau here, and there is a low. This is Bengal Basin, and this is Kopili Fault, and this is some further west to the Kopili Fault, the east. And then we have no much control over here because data is only concentrated here. So let us try to understand the Shillong Plateau structure, high velocity structure, and Kopili Fault. This is continuing up to 30 kilometer depth. This is now the Bengal Basin has come, no more low velocity, come to normal moderate velocity structure, green, and Shillong Plateau is still existing, still higher velocity, and Kopili Fault is very much visible as a low velocity structure, the red, this structure. And as you come to 40 kilometer depth, it shows that at the Kopili Fault end there is a high velocity structure. Means at the fault end there is a high velocity, hard rock is there, and that is accumulating stress, and that stress is getting triggered through Kopili Fault. So studying the source mechanism, studying the B value structure, studying the fractal structure, studying the seismic tomography, we understand that Shillong Plateau earthquakes are pop-up tectonics, a circular type of structure, pop-up tectonics, and Kopili Fault is a transverse structure, and down to 35 kilometers or so, Kopili Fault exists, and below that there is a high velocity hard rock, which is a stress concentrator, which is accumulating stress and getting released through Kopili Fault. Next one, please. I think I have done. Oh no, source zone is still there. So I have talked about the past earthquakes, past large and great earthquakes. The Assam earthquake by strike slip in the syntaxis zones, Shillong earthquakes by pop-up tectonics, by reverse faulting, Kopili earthquakes by strike-slip faulting, long Kopili fault. Even the recent earthquakes Kopili fault has generated, that we have tried to understand the tectonics part of it. Now, most recently earthquakes happened in Manipur. I will give you a little bit more information about that. Then Tripura, 5.7. Then Mizoram, there are many earthquakes, Mizoram. Something like 8 earthquakes within some few months in 1 year. Then Assam earthquake, 6.1. What is their mechanism? How they have occurred? What is their source zone? Next one, please. Now, this is Manipur earthquake. As I already mentioned, the Manipur earthquakes occur here. And there are 2 thoughts. One is by one of my students, ISR. He is Singh, AP Singh. Another is my good friend Galot and his student Kundu. He is doing very good work. Kundu is now Rourkela. So this group, based on their GPS data, they gave a model that this is the structure of the Indian plate, how it is going down below, say, Mizoram, or say this area, this Manipur and this adjoining Indo-Burma ranges. So this is the structure. This is the, they call it CMF. Some Churachandpur. I think I am more comfortable with CMF. So this is the CMF fault. And they said that this earthquake is caused by this CMF. That is their interpretation. They published, I think, where? They published, I don't know where, I should have given the reference. And these people, Singh et al., they published in BSSA. They showed that this is the earthquake, and the green, if you can see, those green dots, the aftershocks are trending towards the Kopili fault, along the Kopili fault. And the earthquakes have occurred by strike slip. So Kopili fault is a strike slip zone. Rupture or aftershocks is along the Kopili fault. So their interpretation is Kopili fault is the source zone for this earthquake. I think it's quite logical. And I would also add that, as I said before, the fault intersections are the very vulnerable zones for earthquakes. So could be that Kopili fault is hitting here, that CMF, and that junction is the source zone for these for these strong earthquakes. So that is the about the Manipur earthquake. Next one. Then came the Tripura earthquake. So such a small earthquake, it caused some liquefaction. It's not actually liquefaction or some sort of liquefaction. So this was also well studied by one student in NIT, Das. He is now doing PhD in IIT Kharagpur. And the earthquake is here. So this in the Bengal Basin is part of Bengal Basin actually. This Tripura here and is part of Bengal Basin. So in this earthquake occurred, and it was 5.7, and yes, this is the study of you can say Panda, Kundu, Galot group. Panda is student of Kundu. They have identified that this Sagaing fault is here at the central part of the this is EBD somewhere here. Sagaing fault is there along the central Burma Basin. So that is the, you can say, accommodating the plate movement by strike slip movement. So they say that the maximum stress of the plate movement is taken up by the Sagaing fault over here. This is that high, gradient they have shown. And another stress, part of stress is also taken by some percentage they have said, is also taken up by CMF. So they said that the CMF is a vulnerable fault and taking up stress. So this is now we have studied this Tripura earthquakes and also the Mizoram, all these recent earthquakes, some 8 or so felt earthquakes occur. All these earthquakes are plotted in the section, and it is shown that all these earthquakes are in this wedge between, you can say, eastern boundary fault and the CMF. So in this wedge, all the earthquakes occur, and they all occur by mostly by strike slip faulting. This is thrust faulting with some strike slip component, and they are almost pure strike slip component. So these earthquakes are shallow earthquakes in the Burma wedge between the eastern boundary fault and the CMF. Next one. So the subduction zone earthquakes are shallow as well as deep, up to down to 200 km in the below in the Burma ranges. I think this is I think again it is shown in a different slide that Mizoram earthquakes, how it damaged that structure, and there are so many felt earthquakes, and something like 11.4 to 4.9, and there are huge earthquakes in Mizoram when PSU called a seminar on this earthquake, and these earthquakes in this way, and as I already explained. So these are this is the this part has suddenly become very active. This west part has suddenly become very active, and whether it is a of course there are earthquakes down depth also, but the earthquake, if the earthquakes are shallow and strong and large, that will be dangerous, because subduction zone earthquakes, even if it is 7.5 or so, most of them are 7 and above, then they will not cause casualties or much damage, because they are much deeper. Deeper earthquakes, naturally it will be attenuated, the waves will be, the energy will be attenuated by the structure to reach to the surface. But if it is shallow in this wedge, and if it is magnitude 7, it can cause havoc in Mizoram or in the adjoining areas. So this is a bit worrying. Let us hope it is deeper earthquake, like the earlier all large earthquakes. But the wedge part below Mizoram, the Indo-Burma wedge part has produced some 8 felt earthquakes, magnitude 5.0 to 5.9. Next one, please. Now we try to see the they call it earthquake swarm. I will come to more details in the precursor studies topic. Here I just touch upon. Myself and Hazarika, Devajit Hazarika, you might have heard, is a fine geophysicist. He is now in Wadia. He was working in Jorhat. Santanu, Devajit are all my students, and they're all doing very good work. So we try to study this, the number of earthquakes, magnitude. Normally you see in catalog, in the global catalog, ISC or USGS or whatever, as I cautioned you, for Biharu study you must check the threshold magnitude. Similarly, magnitude 5 normally catalog is complete, 5 and above. But below 5, global catalog may not be complete. Though they claim 4.5 is above that is complete, but I think there is gap, particularly in the earlier time. Now, lot of students globally and locally has come, so now maybe 4.5 or even 4 they may claim, but earlier data cannot give us 4.5 is a threshold value. So anyway, we have taken consider only the 5 earthquakes, magnitude 5 earthquakes, and every 10 years, possibly every 10 years or 5 years, can you read it?
Every 5 years.
Every 5 years. Every 5 years, we have tried to examine, you can call it seismicity rate, within that box in this area. This Mizoram in particular, and also in this area, we have tried to see how many earthquakes magnitude 5 and above occur every 5 years. That is the way of seeing the seismicity rate, particularly for the larger earthquakes. So we plotted that, and you can see the average earthquake, average number is about 6 or so, 6 or 7 or 6.5. So average number is 6 to 7 earthquakes. Some are low also, less than 5 or less than 6. So this is the average number of earthquakes every 5 years, magnitude 5 and above. 6 average in this box. But in the last 5 years, 15 to 20, there has gone to about 20 earthquakes in 5 years. So this type of activity is called earthquake swarm. The earthquake swarm could be a precursor for a large earthquake. I can say this much, I cannot say when, where, and what magnitude earthquake will occur. Our limitation is up to this. Mizoram could be vulnerable for a, Mizoram or adjoining area could be vulnerable, this block could be vulnerable for a large earthquake, may not be also. It could be false alarm. Next one, possibly I finished. So in summary, I can tell you that 1958 earthquake by strike slip faulting at the syntaxis zone and not at the MHT. MHT means main Himalayan thrust, that plane of detachment, Himalayan model. I did not go to that. So it is not a typical, what I want to say, it is not a typical thrust faulting earthquakes in the Himalaya. Every earthquake is unique. Every earthquake is unique in its own tectonic environment. Bhutan earthquake, they made it a Himalayan earthquake, shallow earthquakes and thrust faulting earthquakes. We found it different. Similarly, this earthquake initially was thought to be thrust earthquake, in the Himalayan plane of detachment or MHT earthquake. Is not, it's strike slip earthquake. 2009 Bhutan earthquake, we infer it could be a Kopili fault earthquake. 2000 Sikkim Himalaya earthquake, I did not go to that, but it is a deeper earthquake, 50 kilometers. It's not a typical Himalayan earthquake. Himalayan earthquake is 20 kilometers and thrust faulting. Sikkim earthquake is 50 kilometers and strike slip faulting. Down to mantle, the stern burst fault is reaching. So Sikkim, then the IBR earthquakes are subduction tectonic. So these are the interplate earthquakes. And the interplate, that's why I already explained, 1897 pop-up tectonics, 1943 and 1869 Kopili fault, 2016 and 2021 Assam earthquake, Kopili fault, 2017 Agartala is also a local strike slip interplate earthquakes, and 2020 Mizoram swarm activity, a precursor with a question mark. And in Bengal Basin, I did not cover much, I did not go in details. There are 2 large earthquakes, and they are by strike slip faulting, and one, again, some Indian seismologist, US seismologist, again from GPS study, they say there is a mega earthquake chance in Bengal Basin, which I don't believe. And Panda et al. Miss Kundu, Gaylord, Panda is a PhD student, he is doing a very good job. After PhD, he has now gone for postdoctoral to USA. So Panda et al., they rule out such possibility of mega earthquake. In the interplate zone, mega earthquake is not the place. Mega earthquake only in the huge subduction zone, huge plate and huge stress. Interplate zone, mega earthquakes you don't expect, but interplate zone we have already experienced great earthquakes and large earthquakes. I think this is the last. So we can take a 5 minutes break or so, and any doubt is there, you can ask me now or you can ask me later. Yes.
So you talked about this movement of plates against the Indian plate against the Asian plate, and also subduction below the Burmese plate. Now, we know that Himalayan plate is about 2,500 kilometers, and it is increasing in height. So will there be a point when there will be an equilibrium because of the sheer weight of this Himalayan plate and the pressure with which this plate is moving against the Asian plate? And will there be an equilibrium when this movement of plate will be distributed because of the weight of the Himalayas, increased weight of the Himalayas?
You have asked a very good question actually. I wish I could explain with slides to all of you. We have published a paper in Nature doing seismic tomography of the whole Indian subcontinent. If you like, I can send you by email. In that we have found, as you say, how long the Himalaya will take up this stress. We find that from the velocity contrast of the northern part of Indian shield and the southern part of the Indian shield, we have come to an inference that the Narmada Reed Basin could be a next subducting zone for the southern sill part. And because that cannot, as you say, cannot take the balance so much, and there will be another subduction zone or whatever may develop along the Narmada Reed Basin. So it's a very good question. I like it. Yes. Any other doubt? Any other query? Yes.
So you said to find the threshold magnitude or cutoff magnitude.
Of course.
Yes, sir. So when I try to find plot the B value, no, so Z map is automatically giving the B value.
Yeah.
MC directly has something around 3.4 or 3.1. So should I also emit the data, or should I have to include more data to rectify those value, or is it correct one?
Normally GMAP that software takes care, but you can also check by least square feet method whether that threshold value which you find from least square method is matching with the GMAP software also. 3.5 I think bit lower side. I would expect 3.5 and above should be the threshold magnitude for B value estimate. So yes, that is one suggestion, and you have pointed out very nicely. So GMAP take care not only by this B value map, also they have done it by GMAP software. You can try that. B value map is very much interpretive than a number. Yes. Any other query? Yes.
Sir,
yes.
I have a question regarding very recently on February, the State Disaster Management Authority, under the influence of MDMA, they have a mock drill, mock drill. That mega earthquake mock drill that estimating 8 magnitude earthquake prediction. So is there any chance of 8 magnitude in and around Mizoram?
Another good question. So far, there is no past records of great earthquakes in the Indo-Burma subduction zone. All are less than 8, 7.2, 7.5, 7.6, although hardly I think. So there are some 25 large earthquakes in the Indo-Burma ranges. So far there is no great earthquakes is recorded so far. It is a very trivial question for me also, how to handle it, because the great earthquakes need a huge stress and a huge structure for this. And of course, this subduction structure, this is not actually, again, yes, you made me remember, this is now there is a controversy about this subduction and strike slip movement. Had it been subduction, if it is an active subduction, then there could have been a possibility of great earthquakes, but active subduction possibly is no more there, because the tectonic stress pattern and other evidences, GPS study and other, and also the focal magnitude study, they reveal that in the Indo-Burma ranges, stress is, the principal stress, p-axis is north-south direction. If there is subduction across Indo-Burma ranges, the p-axis, compressional stress, should be east-west direction. But the compressional stress direction from GPS study as well as from the focal magnitude study is north-south direction. So that is giving one clue that the subducted structure is there. Earthquakes are deeper down to 200 kilometers, but not by active subduction process, but that is due to this dragging of the whole subducted lithosphere to the north. You get my point? So if there had been active subduction, so means real subduction process, if it is there, then 8 would have been possible. But since now it is being dragged up, up to the north, the whole subducted structure below in the ranges being dragged, means to the north due to plate movement, Indian plate movement. So possibility of 8 may not be there, but I may be wrong. But 9 is not there. 9 should not be there. It is only in a oceanic subduction zone. 9 will not be there. 8, but near to 8, 7.5, 7.6 is there. But 8 is not recorded and may not be there. That is my anticipation, but we are not, we cannot say what magnitude.
Okay, now I think we have learned a great deal about earthquake, particularly in Northeast India, from the speaker's vast experience and that research work. It seems that now we are just waiting for the earthquake, which we hope not. Anyway, so let's take a short break, 5 minutes, and then we'll continue the next session. And the Professor will chair the next session. So,
Thank you. Thank you so much. Thank you so much. Thank you.
It's on the way, but I think you can start here while Sir is giving the lecture.
Okay.
He will also take while giving the lecture. So please, Sir, on the stage.
Yes, I think now we have come to your topic, title topic. Where you stand in earthquake prediction and forecast research. Okay, next slide we can go. Now, this study started sometime in 1970s. The whole world almost was involved to predict earthquakes. Including developed countries and many developing countries like ours. So we can talk about, there could be precursor before a earthquake, some signal, physical property changes of earth's crust or earth's interior. That could be short term, few minutes to few weeks. Few minutes means could be annual or something other than that. Sometimes the spring discharge suddenly stops or changes. Or intermediate precursor, few months to tens of years, 10 years, and long term, from tens of years. The long term, I think short term has got some immediate effect, otherwise, months to 10 years, it is of no practical use. Even it is short term, let me tell you frankly, even in short term prediction, suppose I am able to predict earthquakes, how it is going to help you? Will you vacate the whole Aizawl city? Or what about the Aizawl, city property? So I think a prediction, to me, first thing it cannot be done till up to date. Second thing is, even if I am able to predict earthquakes at 10 days, within 10 days a earthquake will occur in Aizawl. For 10 days you will shift the whole city, your whole work, and go to some other place. So it is not of practical use, I suppose. To me, earthquake resilient society is the solution like that of Japan, which I told in my keynote address. So anyway, So the whole world started earthquake precursor study, we also started, and I will show you some results. But even if we made something like, say, about 50 years of research, we are nowhere, thank you so much, we are nowhere to predict earthquakes in terms of time, space, and magnitude. I told you this Kopili fault is vulnerable for a strong or large earthquakes. When it will happen, we cannot say, but we can identify the source zone which can produce large earthquakes. But we cannot say when and where, exactly which spot and when and what magnitude will occur. So with time, space and magnitude, I think I am very clear to you all, we cannot predict. We can forecast to some extent, or rather I should say more scientifically, we can identify the source zone where it is vulnerable for large earthquakes. In 1970s, Rikitake has a very nice voluminous book on earthquake prediction. A lot of research work by that time was there, and he made a very compiled review work on that. And once I was listening to a seismologist, maybe some Iranian seismologist or someone, he was telling that we publish books and millions of research papers, and when the earthquake occurred, it fell on my head in the office. He is showing his books and publications in his office, and he was sitting in that office, and he said that when the earthquake occurred, it all fell on my head. So that is the status of earthquake prediction till as of today. There is another book very recently, my good friend Susan Hoff of USGS, he has named it Predicting the Unpredictable. It is not a really very, with scientific data, it is, I think, more of philosophical aspect. So predicting the unpredictable. Next slide, please. Now, what are the precursors that one can study? Even you can study in Mizoram if you want, in the campus. You have already got one instrument. There are many methods, and one method is already there. You have got the instrument here. So there are geophysical precursors, the changes in Earth resistivity. The Earth's resistivity can change. Gravity value also changes, means microgravity value. Means gravity value at a particular place, with time may change in terms of micro gal. One centimeter per second square is called 1 gal. Then in terms of micro gal, you can measure that with microgrammeter instruments. Then magnetic value means magnetic content of the rocks may change in terms of movement or whatever, fracture zones and flowing of water or whatever. So magnetic value may also changes. In seismological research, the seismicity rate or the earthquake swarm, as I just mentioned, or the B value of a particular place changes with time, or the velocity of the P wave and S wave, the ratio may change, and change in tectonic stress pattern. As I said, that the tectonic stress now, it should have been east-west direction in the Indus ranges, but now it is north-south direction. Possibly over thousands of years, when it was subducting, possibly there was east-west computational stress, but now the subduction possibly ceases and the whole plate is dragging and stress has changed. But that is in terms of thousands of years, geological time. But in terms of tens of years, the tectonic stress pattern change has been observed. The geochemical precursors, that is radon content in soil or water, that also changes. And helium gas in the soil that you can measure, that also changes. They are all observed properties. Most of them we have done. Then geological precursors, change in downwater table, change in spring discharge suddenly stop, spring suddenly stop, or groundwater suddenly, water level in your dug well suddenly goes down by a significant depth, or crustal deformation, some neotectonic activity or some crustal deformation, abnormal changes. And animal behavior, as I already discussed, particularly the underground animals like snakes and rats and other things. Next one. This is from Rikitage's book. The velocity ratio, seismic velocity changes has, with time, it is observed measurements, and it has shown that velocity goes down before a large earthquake, or resistivity goes down before a large earthquake. Water flow changes, it goes up or down. In crustal deformation, through GPS observation, there is sudden change in crustal movement upliftment or subsidence, or horizontal movement, which can be monitored by GPS nowadays. Then seismicity changes, as I already told, the seismicity rate or velocity, lot of changes. So these are observed phenomena, and it is in the book. Next one, please. So I came back sometime in 80s, 83, 84. 84 we started this experiment in Northeast India. So I studied some literature on earthquake precursor studies. I think one of the oldest study might have come across this figure or these authors, Khatri and Weiss, in 1976. They identified that this is the Assam gap, this is the syntaxis zone, lot of activity and great earthquake, Shillong Plateau activity and great earthquake, and this part much less activity, and this is the gap area, I think popularly known as Assam gap, and vulnerable zone for it. That time a gap hypothesis came up. Between two large earthquakes, the zone is there is a gap, no much earthquake, so could be a vulnerable zone for earthquake. Then later on we interpreted to be, a seismic zone. Anyway, so this is one precursor hypothesis was that time came up, and they identified this zone. Then Guha and Bhattacharya, Professor Guha is no more, he is from Pune, mathematician. Bhattacharya, I don't know which Bhattacharya, maybe IMD or I don't know where from. So Khatri was from Roorkee, that time it was Roorkee University. Guha, he tried to see that with time, 63, 1970 and 1978. With time, the B value, I don't know which area, I forgot to mention that. The B value changes with time, and with the lowest B value there was a 6.4 earthquake, one was here 6.7 or whatever. So two earthquakes, strong earthquakes, they correlated with the temporal variation of B value at a particular place, particular area. Then Gupta and Singh, Padma Shri Harsh Gupta is my senior from IIT ISM. Singh, possibly he is BK Singh from Banaras Hindu University. They, estimated the P residual. P residual means when you compute the, when you locate the earthquakes, you give a model, you have got an observed time, and according to your model, computer also compute what the time should be to be taken by this path. So that difference is called residual. So they found that for the Shillong Observatory, it is dependent on the pure velocity or rock velocity, means velocity of the formation changes. So they found that in the Shillong Observatory, the earthquake waves, their residual value has changed with time. So with time, say 1967 to 70, some interval of month or whatever, December or I don't know, August, December or whatever. So they found that there is a sudden change in the residual value, and then there was an earthquake somewhere here. So these were all, starting point of Picasa studies in India, you can say. I have not given those examples because my time is, for 4 topics. So there are also global examples where this type of observations are there in California or in Russia, particularly for the resistivity, California particularly for the BP by VS. There are many global examples you will find in the Rikitake book itself. So these are the Indian study, and I tried to have some knowledge about the Picasa study in India. Then before I started our GSI experiment, next one. So this is GSI experiment from 1984 to 2006 till I was in the chair. We continued some experiment in Shillong and one experiment in Sikkim. So this is the so-called Assam gap. Now we made a Picasa measurement observatory, you can say, in Shillong itself. And there are 2 earthquakes before this, during our experiment. One was Kashar earthquake, managed 5.8 or so, or 6, whatever. This is that solution. Now you understand this is some thrust faulting with some strike slip component. And this is the 1988 this is I think now MW 7.0 or 7.1. So the 1988 earthquake. 2 earthquakes occurred during our experiment, and also this earthquake was very well studied by Gupta and Singh. And these are the 3 different earthquakes for which we have some precursor, and these are the publications which we made from our experiment. Next one. Now this is the experiment we did. We are trying to measure the Earth's resistivity, deep resistivity, not a shallow resistivity. Deep resistivity means your electrode speed should be much more. Current electrode speed something like 3 to 4 kilometer. And we made 2 stations. One is in Shillong Gulf area and one is in Mao Pot. 2 different geological formations. This is hard rock and this is phyllite formation. And in 4 directions, there are reason. In 4 directions, we are measuring we are sending current between 2 electrodes. This is a typical geophysical method. I think there are geophysicists here. So you send current into the earth and measure at another distance point the potential difference due to that sending current at other point, and see every day whether this value of resistivity is changing or not. Earth's resistivity below Ceylon area down to 3-4 kilometers depending on the spread. And we had 2 different type of geological formation was different. Our experiment was a bit unique. That is why it was published in a very good journal. It is good for publication, not good for prediction. So we did this experiment, and this is the electrode configuration, the current electrode and the potential electrode, 2 stations. So at one station, this station Gulf area, we find that among the 4 directions, only 1 direction has shown some lowering of the resistivity value. This is with time, and this is the value. So it started with some low and then went a little bit to normal or high, then it is low, and for some time it was low, and again came up. And other directions, there is no changes. Similarly, at this station where phyllite was there, means bit soft rock compared to Ceylon hard rock, in all the directions there was change. Before the Kachar earthquake, 5.8 magnitude, it was about 80 kilometers away from our observatory. Every day it was manually we are doing. Every day we are taking with our instruments and worker and scientists. We are doing this job. This is very laborious and can't be continued unless it is limited things are made. Anyway, it was initial experiment, and we found that this type of anomaly at station 2 in all the 4 directions there was change. Just before the Kachar earthquake, some 7-10 days before or so, and it continued for some time, and then it came to normal. So it is good, and we analyze this, and then we, of course, there was felt earthquake. It was well known, and then some earthquakes, more earthquakes. We also plotted from Shillong Observatory. We took the information, and we tried to plot and try to see, yes, something is happening before a failed earthquakes. But we did not predict this earthquake. We just tried to understand that before a earthquake, resistivity changes, and that was published. Now, this is another experiment not by us. This was by Survey of India, Arur. Survey of India, they also do gravity survey, with time. Means every 5 years or 10 years, I don't know now, but they do this survey. So in Kachar area, this is the gravity map in Kachar area. This gravity map it's called Bugar anomaly map. It's it's a geophysics subject. So just from me, you just visually you can see this type of contour map is there. Means this is higher value and this is just a contour, and there is some maybe some these are also contour. So the close contour, say higher gravity value or lower gravity means minus, I suppose. So whatever the value is high or low, so there is a close contour, a good structure or whatever is there below Silchar, and this is the epicenter of the earthquake. And that survey was taken sometime, I can't read, but before the earthquake. So before the earthquake, maybe some 5 years before or 2 years before, I don't know. So this earthquake, this map is before the earthquake, this is the map. And after the earthquake, after maybe something like 1886 or so, I can't read. 86. So after 2 years of the earthquake, they again went to that area and to the gravity measurements and find that there is a change in gravity anomaly, gravity contour. So that means it is understood that due to earthquake there is some crustal movement, and there is some change in, this is in microgravity, micro value, not your normal gravity value that 980 centimeter per square. This is, as I said, in micro value measure at a particular place. With time the value changes, and that changes can be explained due to crustal movement or whatever, due to big earthquake or whatever. So this is a change they found. Again, another 2-3 years after, still it is not in that shape. Means there is some permanent crustal changes below the Kachar area. So the message is that there is some precursor or some changes in physical properties of the rocks before and gravity or post after the earthquake. Next one. Now this is another interesting example. Again, it is our study from GSI. Someone was asking microseismicity. We are monitoring microseismicity in Shillong by closed network, by some 5 to 8 portable stations, as I said. That time of course analog. Now it is more easy. It is all digital. So we are making a network every year and recording earthquakes, micro earthquakes. As I said, that micro earthquakes goes in thousands. So lower the magnitude, higher is the number of earthquakes we can record. Some battery is gone or what? This one, no? So can I sit? Yes, I think you can bang the chair. I want to sit. My back is spinning. Yeah. Get here. Okay. Please drag the chair here. Hope this is not disturbed. Yes, that's fine. Yeah.
So there is tea.
Oh, no, I don't take actually milk tea. I can't, it gives me acidity. So I took my tea. I had my black tea, so I am fine. Yes, my back is paining, so I'm sorry. Yes, that's fine. So every year, 6 months, that is GSI typical field work we are doing in Shillong and recording earthquakes. And these are all located earthquakes. And now I am trying to see how many earthquakes in every month or whatever are being recorded. So this data gap is there, means that time we didn't have any network, because all temporary network we take some 6 months data and go to headquarters, analyze them like that. So these data, you can see there is a gap, but you can see still it is interpretable that this is possibly the normal rate of seismicity, something like 20 or whatever, I don't know, earthquakes per month or whatever in the Shillong area. And then suddenly there was very significant change in earthquake activity. Then this gap, maybe data gap, but then this earthquake occurred. This 5.8 earthquake occurred. And then the subsequent field season, we found that again it has come to normal. So what I want to say that before a large earthquake, large or moderately strong earthquakes, felt earthquakes, it was well felt and some casualties was there, some bridge was destroyed. Before that earthquake, there was change in seismicity rate. So that is one observation we made. We tried to understand precursors. We can never predict earthquakes so far. This is one observation. The other observation is, this paper is in pure applied geophysics, a review work. Means whole, we published 3 papers, and all the 3 papers I then combined and made a comprehensive paper, this one. You can have a look. So this is VP by VS, and VP by VS I think you are confusing, or maybe you are right. VP by VS, we normally measure from TSTP, means S minus P time, and P time. That is called Wadati plot. Means it is too technical for other people. Just let me tell you that we can, by some technique, Wadati plot technique, we can find out the Vp by Vs value. Vp, as I said, 1.73 times more than Vs. So that value, 1.70 or 1.72 or 1.78, whatever, that value for a particular area we can measure from our earthquake records, arrival time of P and arrival time of S. So that is called S minus P time plot by P time plot. So from that plot a linear relation is found, and that slope is called, that slope gives us the Vp by Vs value. Anyway, so that Vp by Vs value we estimated, and we found that with time it is, with time the value we have tried to plot, and we can see that again there is a data gap, but we can see there is a trend, the value was lowering and then again it came to normal. So we put with a question mark, we said whether Vp by Vs also changed before that 1984 strong earthquake. So Vp by Vs changes, seismicity rate changes. Then this one is magnetic anomaly. It was, we are trying to, with the fast gauge magnetometer, we are trying every day, we are taking 2 measurements at a particular station in Shillong, at a particular spot. And magnetic value, it fluctuates so much because of the magnetic storm and other. Magnetic measurements is a bit, tricky. So it is, you take reading now and then after, immediately you take another reading, it will vary by 10, 15 gamma value. So magnetic value fluctuates very much, not gravity value. Gravity value is accurate, precise within even 0.1 microgram. So the value was too much fluctuating, 2 readings, and then we take to the average, and with time we try to plot the magnetic value of that particular spot. With time, how it is changing. I don't think we can get any interpretation from here. There is no significant or diagnostic anomaly in magnetic measurement. So it did not work. We also try to measure the water well depth. Every day we are going to the well, dog well, some 3-4 well, and we are measuring the water table. That is typical, hydrological study, and we found we cannot say anything from this measurement. So these 2 measurements, so negative result is also result. These 2 measurements did not produce any precursor signal as such. Next one, please. Then we had microgravimeter in our department. That time it was purchased, and we tried to take microgravimeter traverse. Traverse means along this line, say from Dauki to Bhutan border, that road was there via Guwahati. And along the road, some school, some IB, Inspection Bungalow, or whatever, some permanent structure at a permanent corner, we make a mark. Every 6 months we are coming from GSI, Calcutta, and we are measuring the gravity value in microgal at that particular stations. So this was giving good results, and encouraged by this, we took another 2 traverses. We were, we crossed Brahmaputra river by ferry and all. So we were taking these 3 traverses were started, but unfortunately we could not continue this measurement because of that time there was insurgency problem in Assam. So we gave up. The experiment was abandoned. But what I want to, this is published. What I want to say here, that in the Assam, in the Shillong Plateau we found some 3 measurements, means every 6 months we are taking measure. Every day gravity does not change. So maybe in 6 months or 1 year time or 2 years time there may be some change. So every 6 months we are taking, we found 3 data, we can find there is increasing trend in Shillong Plateau and decreasing trend in the Assam Valley before the 1988 earthquake. So there is some gravity precursors or whatever was observed, though it is with a pinch of salt because data is so poor, 2 or 3 data, 1.5 years experiment or 2 years experiment. So this is the status of our gravity observation in Northeast India. Next one. Yes, here is a success story. Possibly some of you know about this. This is again Professor Gupta. He is Padma Shri Professor Gupta and Singh, Banaras Hindu University, Harsh Gupta. This is, as I said, earthquake swarm. This actually is hypothesis. My guide, my professor in New Zealand, he was very much an earthquake prediction man. Means that time the earthquake prediction research was in a peak, and he is one of them. He made a lot of research and a lot of publications in Nature and all. So he made a hypothesis that there he took the data from Japan, New Zealand and California, 3 countries he has studied, and he came to a hypothesis, I should say, it's a swarm hypothesis, that before a earthquake, large earthquake, there is a swarm activity. That came in Nature publication. So Gupta and Singh, what they did, they studied this something like 5 degree area in Indo-Burma area where that earthquake, 1988 earthquake occurred here, somewhere here. So, this is Kachar. So first they verified this hypothesis of Evison, Professor Evison's hypothesis. It is known as Evison's hypothesis. They tested this hypothesis for the Kachar earthquake. So they found that there is a normal seismicity, very rare, and then suddenly in this time period there is a lot of seismicity, then some fewer seismicity, then the main shock, Kachar earthquake. So they came to a possibly swarm hypothesis works in Northeast India. So that is their test of the swarm hypothesis. Then they took this area, again I think 5 degree by 5 degrees area, and that particular, if you can read the latitude longitude, that is in that occurrence of that earthquake, 1980 earthquake. They took that area and magnitude, I think 5 and above they plotted. So this is their plot, and they find a swarm, then a gap. They took magnitude 6, maybe 6 and above. They also found this swarm. Then they took magnitude more than 6. So from these observations, they made a forecast. In 1986 paper, they made a forecast in technophysics. They made a forecast that within 3 years, a large earthquake is going to occur in this block, 5 degree by 5 degree block or whatever. And he is a very transparent scientist. He said that if it does not occur, then our precursor is a false alarm. Exactly this, I quote, false alarm. It can be treated as a false alarm. And it occurred in 1988. In 1980 it occurred, magnitude 7 magnitude earthquake. Then in 1989, in the same journal, Technophysics, they published this paper and said this has occurred, and our hypothesis, our swarm hypothesis, made this forecast. It is a successful forecast. So this is the successful forecast in Northeast India. It happened. But what is the practical use? For 3 years, you will vacate your Mizoram area of city, Aizawl city. I don't think earthquake forecast or earthquake prediction is going to help the society. If you want to help the society, particularly my message to the civil engineers, that you have to make it sure that the houses are earthquake resilient. Next one, please. This is again, I was that time session in Shillong. We were carrying resistivity and gravity, all these things. Kharsing of NEC. That time he just joined NEC. I don't know where he is now. Might have retired now. So on his own interest, because NEC does not do any scientific work, they are mostly administrative, fund allocation or whatever. So Kharsing was a physics person. He joined the department and he, on his own, he was doing this experiment. Because as I said, in 70s and 80s, Picasso study was a craze for the physicists, for the geophysicists. People were after this. So in his house, after 12 o'clock or after 11 midnight, I think after 12 o'clock, he used to collect the water from his own dug well, because whole daytime it is disturbed. In the midnight, he will collect the water sample or whatever, or mud sample, I don't know. Possibly water sample, he told me. His personal communication, I met him. And he used to measure the radon content of that water. And this is his plot. He plotted this and he found that defined magnitude are given. The 1988 7.3, somewhere 7.5, now it is 7.2 or 7.0 MW. Anyway, the 1988 August earthquake, 6th August earthquake is here, where this fluctuation of radon content is there. So there is a low and then high, and this low is indicative of that is what the geochemists they try to interpret. But if you see some publication on radon content, you will see all zigzag noise like our magnetic anomaly, all zigzag, very difficult to make out whether it is at all a diagnostic anomaly or whatever. Anyway, so his observations of the radon content and during this period, and this is from Kharsing personal communication. I don't think he has published it. I did not publish it also. I just for our knowledge I show this slide. This is one of the interesting radon content slide. Other radon content publication you will see is all so much noise, fluctuations are there. Next one. Yes, this is our last experiment, you can say. Till I was in the chair, I deputed one geophysicist to take gravity measurements along some traverse from foothills to Gangtok. And this earthquake occurred near Gangtok, north of Gangtok, and at that station, near the epicenter of that northernmost station has recorded. With time you can see some it was some 1 month, not this is every 6 months. So yes, 10 months, 20 months, 30 months, 40 months, 60 months. So they found that at the nearest to the epicenter, that station, that fixed station, as I said, they found that the gravity value went very low and the earthquake occurred. So they have nothing to do with the prediction. We have not done any prediction. We have only tried to understand whether there is any precursor anomaly before a large earthquake. And from such anomaly we cannot say when, where and what magnitude earthquake is going to happen. That is the status of earthquake precursor study. Next one. Yes, this MPGO you might have heard. In those days it was DST, now it is MOES. They made it a point that let us make some multi-parameter geophysical observatory to predict earthquakes or to forecast earthquakes, whatever. The first station came in Dehradun, not in Dehradun, from Wadia. They took it, they made it in Guttu. They had proposed 5. One came in Andaman and one has come in Jorhat. I don't know other 2 are where. So because that it started sometime maybe in in 90s, and NEST has started only in 2016, I suppose. So it is a long time they take. Anyway, so these MPGOs are established in different tectonic zone to monitor varieties of geophysical parameters and seismological parameters, radon and all sort of things, multi-parameter. They have got all sort of observations here, and this is, I think, some they have plotted some radon or what? Radon, isn't it? This is so much fluctuation. What you will understand from here? Then this is temperature, this is pressure. So this is rainfall. And they published some paper. They said that an anomaly in radon content in the ground soil and total electron content, TEC, another measurement they have made, and it is, in the ionosphere. In the ionosphere also they have measured this total electric content. So these two measurements, they found some geophysical anomaly, and they have published somewhere. So this is good topic to research for publications, but I don't think in near future we will be able to predict earthquakes. What we can do, we can only make sure to live with the earthquakes. Next one. Yes. I think I have talked about it in my keynote address, but still you can see what has happened, the success and failure story in China. The China, this is 1975 Haicheng earthquake, 7.3. I explained this, and this is the intensity map. I think it is not much clear, and this is the intensity map for the 1976 earthquake. So this earthquake, there are some geophysical precursors or other precursors, but they could not predict. They announced through radio and TV that you vacate your house, seeing the underground insects and other things. So this is the story of two large earthquakes in China, success and failure. They couldn't do anything for the Tangshan earthquake. The whole city destroyed and some 3 million people are killed. Next one. This is Turkey story. Very, very latest, and which is wake-up call our secretary was telling. Turkey is a very interesting situation. There are 3 plates are moving. One is, the Arabian plate, one is African plate, Indian plate is here, and this, they call it Anatolian plate, means, Turkey block, Anatolian plate or whatever. And that plate movement is taken up by the Anatolian fault, and that earthquake occurred on the Anatolian fault. So anyway, the plates are interacting, and the Anatolian block plate is also anti-clockwise. It is also moving due to push of the African plate and the African Arabian plate and the African plate. And that is the tectonic stress is the cause of the earthquake. There is no doubt about that. And 2 earthquakes occur. One is 7.8 and other is 7.5. 2 earthquakes occur, and it is some Dutch scientist from solar system geometry survey, means position of the planets. The geometry of the position of the planets changes, and that can trigger the earthquake. And based on that, again, it's a coincidence or success or whatever you say. He said 7.5 earthquake will hit Turkey and Syria border in 3 days, and that happened. So I was interviewed by the TV and news channel in Calcutta. I said, well, I don't rule out this possibility of triggering due to solar geometry, because also moon geometry changes, not changes, the causes the high tide and low tide in the river or in the ocean. So this may trigger, it can occur as it can act as a trigger, but it is not the cause of the earthquake. Cause of the earthquake is tectonic plate movement. So his I should say prediction has come true, but he also predicted there will be a similar type of devastating earthquake in Himalaya and Indian Ocean. That did not happen. So I don't know what to say about this prediction. So I have just, presented the facts of lives, the facts of China's, facts of Turkey, and what we have done in India. So that is the story, and you see that the whole building totally sank in the ground, and some 50,000 people were killed. So developing countries are, are more vulnerable. Means we are increasing the vulnerability of the casualties with population growth. Next one, I think I have done the job for this one. So part 4, should I continue? You all had tea. Maybe another 20 minutes. Okay.
Okay, sir.
Oh, there will be a different chair. Okay. Okay.
So it's been a nice talk that we have heard. 3 talks, consecutive talk from Professor Kayal. And since the university is situated far from the city, I think the last talk will be shifted for tomorrow. Let's talk. There will be a time for
Okay.
the small talk. Okay. Is there any question from the participant?
Sir, I have no question.
Yes.
About radon as a precursor to predicting the earthquake. So radon is a gas. So what does it has to do anything with earthquake? Is it that release? Is there any release of radon from beneath the surface, and then it increases the content?
Good question. Yes, I think all geophysical anomaly, whether it is resistivity, gravity, of course, mass movement, but there is a high density, they call it dilatancy hypothesis. This precursor, this physical parameter changes due to dilatancy effect in the crust, because when there is a tectonic stress, some micro cracks develop, and that micro cracks causes flow of water or flow of liquid there, and that changes the physical property, means including the resistivity. That the flow of fluid or water can change the resistivity, as you can understand that, or gravity, that due to the movement, mass movement, the gravity can change. Seismicity, of course, due to the tectonic stress and cracking, and some micro tremors are occurring, so that also can change the tremor. So everything, including the radon content, they say this explained by this hypothesis. They call it dilatancy hypothesis. Means before the earthquake occurs, the area develops micro cracks, and that micro cracks causes the physical property change, and the water flow or whatever causes the mud flow, whatever causes the change in the radon content in the soil and water. So that is one way of explanation. Yes. Can I have a picture of the audience? And is there any civil engineers here? Student or engineer? Student engineer?
Civil engineer?
No. Yes. One is there. Could you tell me frankly whether I was understandable to you? Because it's typical geoscience subject, and whether I could give some message to you. Could you understand something from these lectures? Yes? Thank you. Then I am satisfied that I have done some justice to my lectures. Yes.
Okay.
Can I have my camera, my mobile? Yes. I will take a picture of all of you. Yes. Thank you so much. Yes. Just like that. Yes. Thank you so much for your patience listening to me, because whole day you are listening to one lecturer, and that is, I think, hats off to you all. Thank you so much. And I think, oh yes, I have got the thanks slide at the end, so I could not thank Prof, formally. Thank you so much. Thank you so much.
Okay, I'll invite the organizer.
serve. So all audience here and our friends are welcome for tomorrow. Tomorrow we'll have two keynote speakers. So first, led by Professor Kayal, and next will be Dr. Prof. And after keynote address, we will continue by particular presentation. Okay, all of us are invited to attend tomorrow. So then tomorrow we will select a best presentation from the circular presentation. That will be awarded related for each session. Okay, thank you all.